What if the universe isn't alone? What if, right beside the world we inhabit, another universe exists, hidden from our senses, silently unfolding its own story, and we have never even known? At the edge of human understanding, where quantum mechanics reigns with its strange rules and surreal possibilities, a theory emerged both wild and beautiful: the many worlds interpretation. It dared to propose that every choice, every chance, every seemingly insignificant decision splits reality into two, birthing new worlds with every flicker of possibility. Imagine a million versions of yourself scattered across the cosmos, like echoes bouncing endlessly through an infinite canyon. Some of these universes might mirror our own almost perfectly, down to the tiniest detail of a morning ritual, while others are twisted, fractured, and unrecognizably strange. Physicists once laughed at such ideas. They seemed absurd, bordering on science fiction. Yet the universe has a way of humbling us. Particles began behaving as though they existed in multiple places at once, as though reality itself could not be pinned down. Could time flow backwards there? Could stars burn with colors our eyes have never seen? These are not just flights of imagination. A parallel universe, by definition, is a hypothetical realm that exists alongside our own, potentially containing alternate versions of reality. Within these universes, the laws of physics might bend differently, history might have taken other paths, and versions of ourselves might live lives we cannot even fathom. The roots of this idea lie in the very foundations of quantum mechanics and cosmology. According to the many worlds interpretation, every possible outcome of a quantum event occurs, each in its own distinct universe. In one reality, you might be reading these words. In another, you chose to watch a movie instead. Some theorists envision parallel universes as bubble-like pockets within a vast multiverse. Occasionally, these bubbles might collide, leaving subtle imprints on our own cosmos, perhaps even explaining strange phenomena, such as the cold spots detected in the cosmic microwave background. The universe, it seems, may be more like a vast, intricate tapestry of overlapping realities than a single, isolated entity. Parallel universes and alternate dimensions are often confused, yet they are conceptually distinct. Parallel universes suggest complete, separate realities, worlds where different physical laws or histories might apply, and where different versions of ourselves live entirely separate lives. Alternate dimensions, on the other hand, propose additional spatial or temporal layers beyond the familiar three dimensions of space and one of time. String theory, for example, hints that our universe could have up to 11 dimensions, most of them imperceptibly curled up at every point in space. While parallel universes offer wholly separate worlds, alternate dimensions suggest hidden aspects of our own reality, potentially explaining gravity, dark matter, or other cosmic mysteries. Both concepts stretch our imagination and challenge our understanding of reality, nudging the boundaries of science toward realms that feel almost mystical. Several scientific theories lend weight to the possibility of parallel universes. Hugh Everett's many worlds interpretation of quantum mechanics, first proposed in 1957, posits that the universe continually branches into countless alternate realities, each representing a different outcome of quantum interactions. String theory envisions our universe as one among many brains floating in higher dimensional space, each brain a potential universe with its own distinct laws. The theory of eternal inflation suggests that the early universe's rapid expansion never fully stopped, continually producing new bubble universes, each with potentially unique physical properties. While none of these ideas have been directly proven, they create a framework for considering realities beyond our own, expanding our understanding of existence. The evolution of the parallel universe concept traces a fascinating path. Once dismissed as science fiction, it gradually gained scientific credibility alongside the rise of quantum mechanics, which revealed that particles can exist in multiple states simultaneously. Everett's interpretation provided a radical reimagining of reality, proposing that every quantum event splits the universe into multiple branches. Initially met with skepticism, his ideas eventually influenced cosmologists and theoretical physicists exploring multiverse models, string theory, and cosmic inflation. Today, the notion of parallel universes is a serious area of study, explored through mathematical models, simulations, and thought experiments, even if direct evidence remains elusive. At its foundation, quantum mechanics governs this mysterious landscape. The theory describes behavior at the smallest scales, where reality itself seems fluid and counterintuitive. Particles appear to exist in multiple states simultaneously, entangled across vast distances, responding to observation in ways that defy classical logic. These strange behaviors hint at the possibility that the universe is far more intricate than we perceive, a cosmic stage with infinite backdrops. In some realities, choices unfold differently. Histories are rewritten, and events diverge in ways we can scarcely imagine. Entire galaxies might burn in unfamiliar colors, stars may dance to different rhythms, and the very flow of time might be rearranged in these parallel realms. The allure of parallel universes is not just scientific, but profoundly human. It challenges our notions of identity, fate, and the nature of existence itself. Are we the sum of our choices, or are we just one version among countless others? As we explore these ideas through the lenses of physics and cosmology, we confront the mind-bending possibility that the reality we inhabit is only a single thread in a vast, intricate tapestry of infinite worlds. The search continues, driven by curiosity, mathematics, and the relentless desire to understand our place within the cosmos, pushing us ever closer to glimpsing the unimaginable vastness that may lie just beyond the veil of our own universe. One of the most astonishing and mind-bending concepts in quantum mechanics is superposition, the idea that particles can exist in multiple states at once, lingering in a kind of suspended ambiguity until an observation or measurement collapses them into a definite state. This principle, at first glance so abstract and counterintuitive, forms the cornerstone of a radical interpretation of reality known as the many worlds interpretation, first proposed by physicist Hugh Everett in the 1950s. According to Everett, the universe does not settle into a single outcome when a quantum event occurs. Instead, it splits into multiple simultaneously existing realities, each representing a different possibility. Every quantum decision, every flicker of chance, branches off into its own universe, creating an immense, ever-expanding tree of alternate worlds, each a separate cosmos running its own course. Equally fascinating is quantum entanglement, a phenomenon that appears to defy the very limits of space and distance. When particles become entangled, the state of one particle is intrinsically linked to the state of another, no matter how far apart they are, as if a hidden thread connects them across the cosmos. Some theorists propose that entanglement might not be confined to our own universe, but could stretch across multiple universes, forming a vast web of interconnected realities. This tantalizing possibility hints at a multiverse in which all matter, energy, and events are interwoven in ways that challenge our classical understanding of causality and connection. Quantum fluctuations, minute variations in energy that occur spontaneously in empty space, play a pivotal role in cosmological theories of parallel universes. These fluctuations are thought to have ignited the Big Bang, giving birth to our universe. And some cosmologists speculate that such fluctuations continue to spark the creation of entirely new universes in a process known as eternal inflation. Each bubble of creation, a universe in itself, may possess its own unique laws of physics, constants, and structure. The result is a staggering, potentially infinite multiverse, a cosmos so vast and complex that the human mind struggles to grasp its full magnitude. Parallel universes, sometimes described as separate realms of existence, might mirror our own world with subtle differences, or they could be wildly divergent, governed by entirely different physical laws and realities. Some scenarios propose that, for every decision we make, a universe exists where the opposite choice occurred. A single choice in one universe, what shirt to wear, what path to take, gives rise to a branch in another, a new timeline unfolding in isolation, yet inextricably linked through the framework of quantum possibility. Others envision a multiverse resembling a cosmic foam, universes bubbling into existence alongside one another like soap bubbles, each a self-contained cosmos with its own trajectory. The many worlds interpretation remains a provocative and hotly debated concept, offering an elegant solution to some of quantum mechanics' most perplexing paradoxes without invoking additional assumptions. Yet, it also confronts us with the staggering implication of an infinite number of universes, a reality where every conceivable outcome has its own domain. Critics question whether such an infinite proliferation of realities is plausible, while proponents marvel at the conceptual clarity it brings to the otherwise enigmatic quantum world. The allure of parallel universes extends far beyond theoretical physics into the realm of popular culture. Writers such as Philip K. Dick and Michael Crichton have constructed intricate stories exploring the consequences of alternate realities, while television series like Fringe and Rick and Morty bring these parallel worlds to life, allowing characters to traverse different versions of their own universe and confront questions of identity, morality, and destiny. In film, movies like The Matrix and Interstellar visualize alternate dimensions, bending time, space, and perception to immerse audiences in experiences that challenge the very fabric of reality. Comic books, too, explore multiverses extensively, depicting parallel worlds where different versions of beloved characters coexist, interact, and sometimes collide, enriching narratives with a kaleidoscope of possibilities. Despite the rich tapestry of imagination surrounding parallel universes, common misconceptions abound. Many assume that these universes are mere replicas of our own, differing only in trivial details. In reality, if parallel universes exist, they might possess entirely different physical laws, forces, and constants, forming realities that are almost incomprehensible to us. Travel between these universes, a staple of science fiction, remains firmly beyond our technological grasp, as the barriers separating distinct realities are likely insurmountable. The notion that parallel universes provide a resolution to quantum uncertainty, with every outcome realized somewhere, represents just one interpretation, the many worlds perspective, and is far from a universally accepted explanation. In a universe unlike our own, even fundamental forces could be drastically altered. Gravity might be stronger, compressing space-time and hastening the formation of stars and planets, resulting in a cosmos that is denser, faster evolving, and radically different from the one we inhabit. Variations in other physical constants could create worlds where matter behaves in strange and unfamiliar ways, where the chemistry of life is altered, and where the very concept of existence takes on forms beyond our imagination. Each parallel universe, therefore, is not just a mirror of ours, but a window into the infinite potentialities of reality, a testament to the boundless creativity inherent in the quantum fabric of the cosmos. As scientists probe deeper into these enigmas, the interplay between quantum mechanics, cosmology, and the multiverse continues to expand our understanding, inviting us to ponder realities both strange and beautiful, and to consider that our universe may be just one among countless others, each humming with its own possibilities, its own histories, and its own mysterious paths through the cosmos. Conversely, if gravity were weaker, a universe might emerge in which matter struggles to come together, leaving vast stretches of emptiness where galaxies could never fully form. Stars might flicker weakly, unable to ignite the fusion processes that bring warmth and light, while planets, if they formed at all, could lose their atmospheres to the void, rendering life as we know it virtually impossible. Imagine a universe where gravity is uneven, fluctuating from one region to another, creating a cosmic tapestry of dense matter clusters interspersed with enormous empty voids. In such a universe, the elegant orbital patterns of planets and the rhythmic rotations of stars would give way to chaotic celestial dances, with matter moving unpredictably and structures forming only temporarily before dispersing. Similarly, the speed of light, a constant in our universe at approximately 300 million meters per second in a vacuum, might vary drastically in a parallel realm. A faster speed of light could allow information and energy to traverse space almost instantaneously, binding distant corners of the universe more closely than we could ever imagine. Conversely, a slower speed of light might produce a languid cosmos, where cause and effect lag behind, and events unfold with a kind of cosmic hesitation. This shift would not only influence how quickly light travels, but could also fundamentally alter the relationship between mass and energy. Einstein's iconic equation, E equals mc squared, might take on a new form, reshaping the rules of matter formation, star creation, and potentially even the emergence of life itself. Changes in light speed could also ripple outward to the very expansion of the universe, dictating whether it grows swiftly, lingers in slow motion, or oscillates through cycles of contraction and expansion unlike anything we experience. The strong and weak nuclear forces, invisible yet essential architects of matter, could also differ in intensity or function. The strong nuclear force, which binds quarks within protons and neutrons, could operate with altered vigor, reshaping the structure of atoms and the elements they form. The weak nuclear force, responsible for radioactive decay and nuclear fusion, might transform stars' life cycles or even permit exotic forms of matter to emerge. In some universes, these forces could act in ways entirely alien to our physics, creating worlds where chemistry behaves unpredictably and the periodic table as we know it ceases to exist. Moreover, parallel universes could harbor extraspatial dimensions beyond the three we inhabit. Some theories, including string theory, suggest the existence of hidden dimensions curled tightly beyond perception. In these hypothetical realms, the fabric of reality could be unrecognizable. A universe with just two spatial dimensions might prevent complex atoms and life itself from forming, while one with 10 or more dimensions could host phenomena that defy comprehension. Imagine seeing all sides of an object at once, or structures that fold through space in ways our minds cannot visualize. Such dimensions would reshape gravity, energy, and matter interactions, producing a cosmos with entirely different physical laws. Thermodynamics, the science of heat, energy, and entropy, might also vary dramatically. In a universe governed by altered thermodynamic rules, perpetual motion could be possible, or entropy, the gradual tendency toward disorder, might not exist at all. Cause and effect, normally bound by the arrow of time, could operate unpredictably. Events could precede their causes, or contradictory outcomes might coexist, creating a reality where logic itself is flexible and mutable. Time could loop, twist, or stretch in ways that make our understanding of history and consequence irrelevant. In a universe dominated by stronger gravity, stars and planets would form rapidly, often as massive, ultra-dense objects. Black holes could dominate the cosmic landscape, with light struggling to escape their grasp, creating an ever-dark, compact cosmos. On the other hand, weaker gravity could leave the universe cold, diffuse, and starless, a shadow of the luminous reality we inhabit. Variations in gravity, nuclear forces, speed of light, dimensionality, and thermodynamic laws collectively illustrate the staggering diversity of possible universes, highlighting the delicate balance of physical constants that shape our reality, and hinting at worlds where the rules we consider fundamental might bend, twist, or disappear entirely. The possibilities of these alternate realities stretch the imagination, opening the door to a multiverse of untold strangeness. A parallel universe might see elementary particles arranged differently, fundamental forces behaving unpredictably, or even time itself unfolding as a nonlinear tapestry. The interplay of these variables could give rise to entirely alien forms of matter, life, and cosmic evolution. Each alteration, from light speed to gravity, from nuclear forces to dimensionality, offers a glimpse into universes where the familiar laws of physics are supplanted by novel, bewildering rules, demonstrating just how vast, strange, and wondrous the cosmos might be beyond our own perception. However, in parallel universes, the rules that govern reality could be astonishingly different, stretching beyond the limits of human imagination. Theoretical physicists speculate that these alternate realms might host entirely distinct families of elementary particles, with properties and behaviors unlike anything known in our cosmos. In such universes, the building blocks of matter, the quarks, leptons, and perhaps entirely novel particles, could interact under laws we cannot even begin to conceive. Some universes might contain additional types of quarks or leptons, while others could harbor wholly unprecedented categories of particles, giving rise to forms of physics, chemistry, and life that defy our understanding. The fundamental laws themselves could vary. In one universe, there might be an additional force supplementing the four we know: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. While in another, gravity itself could be absent, leaving matter unbound and celestial structures impossible. The repercussions of such differences at the particle level would cascade through all scales of reality, shaping cosmos with properties completely alien to our own. By exploring these possibilities, scientists are not only challenging the boundaries of theoretical physics, but also gaining insights into why our universe is the way it is, offering glimpses into deeper truths about existence itself. In a universe where the strength of electromagnetism deviates from our familiar value, the very fabric of reality would warp dramatically. Stronger electromagnetic forces would bind electrons tightly to atomic nuclei, shrinking atoms and creating dense materials, while chemical reactions would proceed along entirely new pathways. Stars could burn hotter and faster, dramatically altering stellar life cycles and the synthesis of heavy elements. In contrast, weaker electromagnetic forces would produce larger, more diffuse atoms, with fragile chemical bonds that might prevent the formation of complex molecules crucial for life. Stars might fail to ignite at all, leaving vast, dark, frozen expanses devoid of energy. The interaction between light and matter would also be fundamentally altered, reshaping how information travels across space and influencing the formation of galaxies, planets, and cosmic structures. Even the so-called constants of nature that appear immutable in our universe could vary in parallel realities, producing dramatic consequences. The fine structure constant, which governs electromagnetic interactions, determines whether atoms hold onto their electrons or lose them with ease. Slight deviations could prevent complex molecules from forming or destabilize matter entirely. The strong nuclear force, responsible for binding quarks into protons and neutrons, must also remain finely tuned. Too weak, and atomic nuclei would disintegrate. Too strong, and all matter might collapse into heavy elements, eliminating hydrogen necessary for stars. Alterations to the weak nuclear force could modify radioactive decay and the processes powering stars, reshaping the abundance of elements vital for life. These delicate balances reveal how astonishingly precise our universe must be to support the rich diversity of matter that surrounds us. Time itself, a dimension so fundamental to our experience, could behave in radically different ways in parallel universes. While we perceive time as flowing inexorably from past to future, a parallel universe might lack a defined temporal direction entirely, allowing events to unfold backwards, sideways, or in oscillating patterns. Time might advance at vastly different rates, so that what we consider a second could span years or millennia elsewhere, or eons in our universe might pass in an instant in another reality. Such variations would fundamentally alter evolution, technology, and cosmic development. Concepts of causality and determinism could be reversed or meaningless, with effects preceding causes or events occurring spontaneously without any apparent reason, producing a reality nearly incomprehensible from our perspective, yet entirely normal within its own domain. Even the Higgs field, responsible for imparting mass to particles, could take on a different value in alternate universes. A stronger Higgs field would increase particle mass, altering atomic structure, compressing electrons closer to nuclei and producing larger atoms. Stars would form more rapidly under enhanced gravity, but their fuel would burn out faster, accelerating the aging of that universe. Conversely, a weaker Higgs field would produce lighter particles, potentially destabilizing matter and preventing the formation of planets, stars, or life. Each of these variations demonstrates how delicate and finely tuned the balance of physical laws must be, and how any alteration could generate a universe both magnificent and alien, with structures, processes, and possibilities that challenge every assumption we hold about reality. In exploring these parallel worlds, we confront the extraordinary breadth of cosmic potential. From the minutiae of particle interactions to the sweeping arcs of galactic evolution, every element, every force, every constant, every flow of time can be imagined differently, revealing the boundless creativity inherent in the fabric of existence itself. The mind stretches to contemplate universes where matter, light, and life evolve under entirely new principles, emphasizing the profound mystery and grandeur of what could exist beyond the narrow confines of our own cosmic home. Conversely, if the Higgs field were weaker, particles would be significantly lighter, fundamentally altering the very nature of matter. In such a universe, atoms might stretch out, with electrons orbiting far from their nuclei, making stable atomic structures rare or entirely impossible. Without stable atoms, molecules could not form, and the complex chemistry required for life as we know it would be unattainable. Stars, too, might struggle to ignite, failing to sustain nuclear fusion and leaving the cosmos a frigid, dark expanse. The precise value of the Higgs field, along with other fundamental constants, appears finely tuned to allow the emergence of life, hinting that even slight deviations could yield a universe utterly alien and inhospitable to any familiar form of life. In such a parallel universe, galaxies could take radically different shapes and evolve along entirely unexpected paths due to shifts in physical laws and constants. Dark matter, a silent architect in our cosmos, might be absent or behave unpredictably, stripping galaxies of the gravitational scaffolding needed to form coherent structures. Without its pull, galaxies could grow slowly, their shapes diffuse and irregular, while variations in gravitational strength could further warp their development. Stronger gravity might compress matter into tight, dense clusters, whereas weaker gravity could allow galaxies to drift loosely, sprawling across space in ghostly formations. Star formation would also vary, potentially producing regions dominated by either exceptionally young or ancient stars, dramatically changing the visual and chemical character of these galaxies. Elemental abundances could shift as well, shaping stars and planets in unfamiliar ways. A universe richer in heavy elements might favor rocky planets, raising the odds of habitable worlds, while one lacking these elements might see barren expanses of gas giants or molten landscapes. Cosmic expansion could follow a different tempo, altering how galaxies collide, merge, or remain isolated. Faster expansion might create lonely, scattered galaxies, while slower expansion could foster more frequent collisions, forging complex galactic networks unseen in our own cosmos. These variations underscore the delicate interplay of forces and constants that have sculpted our universe. Without dark matter, the universe would lose the majestic architecture we recognize. Galaxies as dense, spiral, or elliptical forms might not exist. Matter would remain more evenly spread, stars and planets scattered in a cosmic fog rather than gathered into intricate clusters. Massive structures such as galaxy clusters or superclusters would vanish, and the cosmic web of dark matter filaments connecting galaxies would be absent. This would fundamentally alter the flow and distribution of matter and energy across the universe, therefore changing everything from the formation of stars to the evolution of galaxies. Expansion could accelerate, unimpeded by dark matter's gravitational restraint, potentially hastening scenarios like heat death or the Big Freeze. Stars themselves might lead astonishingly different lives in these alternate realities. If gravity were stronger, stars would consume their fuel rapidly, burning out in comparatively brief lifetimes. Weaker gravity could produce stars with incredible longevity, persisting far longer than any we observe. Variations in elemental composition or nuclear forces could drastically reshape stellar evolution, creating stars that bypass familiar phases or produce entirely different elements. Without the strong nuclear force functioning as it does in our universe, stars might fail to forge the complex elements necessary for life, or they could generate entirely new chemical landscapes, producing a cosmos whose biology, if it existed, would be beyond comprehension. Black holes in such universes might defy every expectation. Instead of consuming everything, they could repel matter and light, carving immense voids and pushing galaxies apart. Some might radiate prodigious energy, transforming into cosmic beacons that bathe the universe in light and radiation, potentially powering advanced civilizations with seemingly limitless energy. Event horizons could become permeable, letting information and matter pass freely, solving paradoxes that challenge physicists in our own universe. These black holes could recycle matter, breaking it into fundamental components and redistributing it, establishing networks of energy that define cosmic architecture in entirely new ways. Galaxies might cluster along channels of energy rather than gravitate towards singular massive points, producing webs of radiant light threading across space. Even the cosmic microwave background, the faint echo of the early universe, could vary dramatically. In our universe, its delicate uniformity with tiny fluctuations seeded galaxies and cosmic structure. In a parallel cosmos, variations in initial conditions could yield a background of light that differs in intensity, structure, or composition, reshaping the entire history of cosmic evolution. The universe could emerge as a realm of unrecognizable landscapes, exotic stars, and bizarre structures, a testament to the mind-bending diversity possible in alternate realities. These imagined worlds illuminate the fragile balance of physical laws in our own universe and the extraordinary possibilities that lie beyond the veil of what we can observe. However, in alternate universes, the cosmic microwave background could unfold a dramatically different tale, revealing realities where the earliest moments of existence were far more chaotic or strikingly serene than in our own universe. Some of these universes might display a cosmic microwave background with enormous temperature fluctuations, signaling a tumultuous infancy marked by rapid, violent shifts. These intense variations could accelerate the formation of massive cosmic structures, producing a realm dominated not by the galaxies we recognize, but by gargantuan black holes that consume light itself. In contrast, a universe with a remarkably uniform cosmic microwave background might struggle to form any substantial structures at all, lingering instead as a diffuse sea of scattered particles, stretching across an emptier, quieter expanse of space. The overall temperature of the cosmic microwave background could differ widely between universes. A hotter background might indicate slower cosmic expansion, allowing energy to linger longer and structures to evolve more gradually, while a cooler background could hint at a universe that ballooned outward rapidly, leaving less time for matter to coalesce. These temperature differences would profoundly shape the unfolding timeline of cosmic evolution, determining when stars ignite, galaxies coalesce, and the very framework of space-time solidifies. Polarization patterns within this ancient radiation might vary as well, offering glimpses into alternate physics during inflation. These subtle imprints could reveal exotic particle interactions, unseen forces, or even hidden spatial dimensions, turning the cosmic microwave background into a window through which each universe's foundational rules are exposed. The universe's expansion rate wields enormous influence over its entire structure. A faster expansion would limit gravity's ability to draw matter together, producing a cosmos scattered with sparse galaxies and isolated stars, with clusters struggling to form. Conversely, a slower expansion allows gravity more time to sculpt the universe's contents, fostering densely packed galaxies and frequent stellar collisions, increasing the production of heavy elements that enrich the cosmic landscape. Expansion rate also dictates the universe's ultimate fate. A sufficiently rapid expansion might culminate in a big rip, tearing apart even atomic structures, while a slower rate could reverse the cosmic tide, ending in a big crunch. Human existence itself is entwined with this balance. Even small deviations could prevent life from emerging, underscoring the delicate fine-tuning of our cosmos. Parallel universes might host entirely different types of cosmic voids, those vast, near-empty expanses between galaxies. In our universe, voids form naturally as matter coalesces under gravity, leaving empty bubbles between dense clusters. Yet in a universe governed by stronger gravity, voids might shrink, packed tightly as matter collapses more aggressively, while weaker gravity could produce enormous, diffuse voids that stretch endlessly. Some universes might have no voids at all, favoring an almost uniform matter distribution, while others might contain voids rich with exotic matter or unusual fields. The large-scale structure of these universes would vary wildly, with each cosmic void shaping the rhythm of galaxies and clusters in ways unimaginable to us. Galaxy clusters, the largest gravitationally bound structures in our universe, could be drastically different elsewhere. In a universe with weaker gravity, galaxies might drift in isolation, leaving space far more uniform and empty than our familiar cosmic web. A universe with stronger gravity could give rise to superclusters of unimaginable scale, cradling millions of galaxies in dense, luminous networks, turning the night sky into a blaze of countless celestial beacons. The interplay of dark matter, cosmic inflation, and fundamental constants could produce filaments, spherical clusters, or entirely new cosmic arrangements, revealing the infinite variety of large-scale structures possible across the multiverse. The elemental makeup of a parallel universe could also diverge dramatically. Stellar nucleosynthesis, radioactive decay, and cosmic ray spallation hinge on the strengths of fundamental forces and the values of physical constants. If the strong nuclear force were slightly weaker, heavier elements might be scarce, leaving a universe dominated by hydrogen and helium. A stronger weak force could accelerate the production of elements like iron, gold, and uranium, creating worlds rich in exotic matter. Initial cosmic conditions, including expansion rate and density fluctuations, would dictate the formation of stars, galaxies, and ultimately the distribution of elements, resulting in universes with chemical compositions alien to our own. Quasars, those dazzling beacons powered by supermassive black holes, could assume forms beyond our comprehension. In a universe with stronger gravity, quasars might be extraordinarily intense and compact, radiating unimaginable energy, while weaker electromagnetic forces could render them faint or even non-existent. Some universes might never birth stars or galaxies, eliminating quasars entirely, whereas others could host exotic energy-emitting structures functioning as quasar analogs under unfamiliar physics. Exploring such possibilities illuminates not only the diversity of potential cosmoses, but also the precise balance of forces that allows quasars to shine in our universe. On Earth, axial tilt shapes climate, seasons, and life itself. R23. 5-degree tilt produces the familiar rhythm of spring, summer, autumn, and winter. A tilt of 45 degrees or more would magnify seasonal extremes. Summers scorched with prolonged sunlight, winters plunged into freezing darkness, polar regions oscillating between unending day and night. Extreme axial tilts would intensify storms, destabilize ecosystems, and challenge human survival. Without tilt, seasons vanish, leaving unchanging climates where equatorial regions remain sweltering and poles frozen, biodiversity diminished, and atmospheric circulation altered. Plate tectonics also sculpt our planet. Without it, landscapes would flatten, mountains vanish, ocean trenches disappear, and the seafloor would stretch evenly beneath shallower seas. Carbon recycling through tectonic activity would halt, risking atmospheric carbon dioxide buildup and triggering runaway greenhouse effects akin to Venus. Life and climate as we know them would be profoundly reshaped, illustrating how planetary dynamics govern habitability and the very rhythm of existence. In every corner of the cosmos and on every world, minute variations in physical laws, initial conditions, or cosmic processes yield universes and planets that defy imagination. From turbulent radiation backgrounds to alien quasars, from giant superclusters to flattened continents, each possibility reveals the delicate and astonishing interplay of forces that make our universe both unique and incomprehensibly rich. Furthermore, without the relentless churning and recycling of Earth's crust, our planet's surface would appear ancient and static, a landscape dominated by rocks that have endured virtually since the planet's fiery birth. Volcanic eruptions and the ceaseless subduction of tectonic plates act as nature's renewal system, constantly replacing old minerals with fresh formations. Remove this process, and Earth would be a mineral-poor, worn-out world, its landscape stunted and its potential for life severely constrained. Life, in all its diversity, owes much to this ongoing renewal, as nutrient-rich minerals from volcanic soils fuel ecosystems from the smallest microbes to sprawling forests. Earth's relationship with its singular moon is a delicate, finely tuned cosmic partnership. Multiply the moons or remove it entirely, and the rhythms of life as we know them would shift dramatically. With several moons tugging at our oceans, tidal patterns would become erratic, producing waves of unpredictable intensity. Coastal habitats could be regularly ravaged, and marine species that rely on steady cyclical tides for breeding or feeding would face chaos. Conversely, without the moon, Earth would spin faster, shrinking our days and altering climate patterns in ways that could destabilize ecosystems. The moon stabilizes the tilt of Earth's axis, granting us the predictable seasons that underpin agriculture, migration, and reproduction cycles. Without this stabilizing force, Earth's tilt could wobble erratically, creating sudden climate swings so severe that species might struggle to survive. No moonlight would leave nocturnal hunters and navigators disoriented, while the absence of tidal forces would disrupt ocean currents, altering the flow of heat and nutrients around the globe, reshaping entire marine ecosystems. The type of star around which Earth orbits further dictates the possibilities for life. Our yellow dwarf sun provides the perfect balance of energy, warmth, and stability. A red dwarf star, cooler and smaller, would draw Earth into a close orbit, locking one side in eternal daylight and the other in endless night. Life would be forced to adapt to scorching heat and freezing darkness, limited to narrow bands of survivable climate. A blue giant, by contrast, would require Earth to orbit much farther out to avoid incineration, extending years and slowing seasonal cycles. Its intense ultraviolet radiation could demand a dramatically enhanced ozone layer or other protective measures. Different stellar light affects photosynthesis, growth, and the chemical makeup of the atmosphere, while stars with shorter lifespans may not offer the stability needed for complex life to emerge over billions of years. Active stars could bombard Earth with flares and coronal ejections, gradually eroding the atmosphere and threatening habitability. Earth's magnetic field is another invisible guardian, a shield deflecting harmful cosmic rays and solar winds. Strengthen it, and areas once hostile to life, including high altitudes or low orbit, could become viable habitats, though migratory animals relying on magnetic cues could lose their way, disrupting ecosystems. Weaken it, and the planet becomes vulnerable. Mutations increase, technological infrastructure suffers, and prolonged exposure could strip away the atmosphere, mirroring the fate of Mars. The magnetic field also paints the sky with auroras, and changes in its strength would shift their frequency, brightness, and location. In a parallel universe, Earth's atmosphere could be unrecognizable. A sky choked with carbon dioxide and methane would intensify the greenhouse effect, heating the surface and acidifying oceans. A thin, helium or hydrogen-heavy atmosphere would let solar radiation pour down unchecked, sterilizing the land. An atmosphere rich in sulfur compounds might shroud the planet in yellow clouds, drenching the surface in corrosive rains and carving bizarre, eroded landscapes. Each variation reshapes climate, weather, and life itself, determining which organisms can survive, evolve, and thrive. Oceans, too, are Earth's regulators. Vast seas absorb heat, stabilize the climate, and house immense biodiversity. Enlarge them, and water dominates the surface, reducing habitable land, intensifying storms, and shifting ocean currents. Shrink them, and deserts expand, climates dry, temperatures fluctuate more wildly, and marine ecosystems collapse. Either extreme disrupts the carbon cycle, oxygen production, and the intricate balance that sustains life on the planet. Earth's orbit defines its year, and any change would ripple through every living system. A shorter year compresses seasons, confounding plant growth, migration, and agriculture. Longer years stretch seasons into extremes, baking summers and freezing winters, risking mass extinctions for species unable to adapt. Orbital changes would also interact with Earth's axial tilt, magnifying shifts in daylight, temperature, and seasonal patterns, creating a world far harsher and less predictable than the one we know. Deep within Earth's core, a swirling sphere of iron and nickel underpins life itself. Replace it with lighter elements like silicon or magnesium, and Earth's gravity weakens, its ability to retain an atmosphere and oceans falters, and habitability becomes uncertain. The core generates the magnetic field. Alter its composition, and that shield could weaken or vanish, exposing the surface to relentless cosmic and solar radiation. Life, as we recognize it, depends on this molten heart to maintain the planet's structure, climate, and protective envelope. A reminder that every layer of Earth, from core to crust, moon to sun, works in delicate concert to sustain the intricate web of life. Furthermore, the intense heat generated deep within Earth's iron-nickel core drives a series of colossal, ceaseless processes that shape the very fabric of our planet. This molten engine fuels the movement of tectonic plates, sparking volcanic eruptions that recycle essential elements and sustain life on a global scale. A core made of different elements could fail to produce this vital heat, leaving the planet geologically inert, its surface static, its landscapes frozen in time, and its ecosystems deprived of the dynamic energy that supports biodiversity. In an alternate universe, Earth's climate could function in astonishingly alien ways. Imagine an atmosphere dominated by methane rather than nitrogen and oxygen. Such a radical change would completely transform the way heat is trapped, redistributed, and released across the globe. The greenhouse effect would intensify dramatically, scorching the surface under relentless heat while generating storms of unimaginable ferocity. Rain, composed of liquid methane, could carve rivers and fill oceans, mirroring the hydrocarbon seas of Saturn's moon Titan. In another scenario, a weakened magnetic field might leave this parallel Earth exposed to relentless solar radiation. Day and night could alternate with extreme temperature swings, while unpredictable shifts in climate sweep across the planet. Over time, Solar winds could erode the atmosphere itself, triggering long-term cooling that alters every ecosystem. The planet's axial tilt might diverge wildly from our own, producing extreme seasons with blistering summers and winters of brutal cold, or conversely, a nearly absent tilt could erase seasonal variation entirely, leaving the climate locked in static zones year-round. Such variations illustrate how even minute planetary differences can create worlds of astonishingly diverse climates. Life as we recognize it depends on the extraordinary architecture of deoxyribonucleic acid, or DNA, a molecule built from 4 nucleotide bases: adenine, thymine, guanine, and cytosine. These bases pair in precise ways to encode the genetic blueprint of every organism on Earth. But envision a reality in which nature selected an entirely different set of base pairs. DNA could then code for alternative amino acids, producing proteins with unfamiliar structures and functions. Life forms might emerge with biochemical systems unimaginable to us, thriving in environments that would be fatal to Earth-based organisms. Laboratory experiments have already synthesized DNA with expanded or alternative bases, proving that genetic systems can be more versatile than nature's standard 4. Such synthetic molecules hint at the possibility of life forms with extraordinary abilities, entirely new biological architectures, and novel adaptations. The implications extend to astrobiology, suggesting that extraterrestrial life could rely on completely different genetic frameworks, fundamentally challenging our definitions of life and reshaping our strategies for detecting it across the cosmos. In a parallel universe, evolution could follow paths beyond our wildest imagination. While natural selection and genetic variation might remain central, the chemical and environmental canvas could redefine the course of life. Consider a world where silicon, not carbon, forms the basis of biological structures. Organisms might possess wholly alien anatomies and metabolisms, with mutation and adaptation occurring at rates dictated by the stability of their genetic substrates. Elevated background radiation could accelerate evolutionary change, while crushing gravitational forces could sculpt life forms built to endure immense pressure. In arid worlds, organisms might extract water from rocks or generate it internally, and the concept of species could blur as genetic information flows freely between otherwise unrelated organisms, creating an intricate web of interconnected evolution. These scenarios demonstrate that evolution is not fixed. It is a fluid, context-dependent process, profoundly influenced by the unique conditions of each universe. Photosynthesis, the process that captures solar energy to sustain life on Earth, primarily utilizes red and blue wavelengths of light. But what if a planet's flora had evolved to harness different colors of the spectrum? Entire ecosystems would transform. A world where plants absorbed green light would no longer be covered in green fields and forests. Instead, landscapes might shimmer in vivid reds or deep blues. Beyond mere aesthetics, such a shift would alter photosynthetic efficiency, influencing plant growth, energy production, and the availability of resources for herbivores. Predators dependent on these herbivores would experience cascading effects, creating ecosystems fundamentally distinct from those on Earth. Every branch of life would be entwined with these changes, demonstrating how even subtle variations in energy capture could reshape the structure of an entire biosphere. Across these possibilities, from molten cores to alternate atmospheres, from exotic genetics to alien photosynthesis, the universe reveals itself as a theater of endless variation. Every planetary parameter, every molecular choice, every shift in light or gravity carries the potential to craft realities both familiar and utterly unimaginable, challenging our understanding of life, evolution, and the forces that sculpt worlds. Moreover, the shifting requirements for light absorption could drastically alter the regions where plants manage to survive, potentially redrawing the map of vegetation across the globe. Forests, grasslands, and deserts might transform as new light conditions favor certain species while limiting others. Such a profound change in photosynthesis would ripple outward, affecting ecosystems, climate, and even the atmospheric composition over millennia. For scientists studying astrobiology, this is particularly significant. The search for extraterrestrial life often hinges on detecting processes similar to photosynthesis, using Earth as a template. If photosynthesis can operate under a broader range of wavelengths than previously imagined, It would expand the criteria for identifying life on distant worlds, suggesting that planets previously considered inhospitable might actually host complex biological activity. Life on Earth, built on carbon chemistry, is only one possibility among many. Other elements, like silicon, possess chemical traits similar to carbon and could theoretically form stable, complex molecules capable of supporting life. In alien environments vastly different from our own, such as the methane lakes scattered across the surface of Saturn's moon, Titan, life might rely on liquid methane rather than water as a solvent, fundamentally altering cellular chemistry. These alternative biochemistries could yield organisms with structures and functions that defy terrestrial expectations, creatures that extract energy from hydrogen instead of oxygen, or cells enclosed in membranes made from silicon-based compounds rather than lipids. They might thrive in extreme conditions that would be instantly lethal to Earth-based life, from sulfuric acid clouds to hydrothermal vents on ocean worlds far from the sun. The possibilities extend beyond elemental swaps. Life could encode genetic information in forms entirely alien to DNA or RNA, transmitting hereditary instructions through mechanisms humans have yet to conceive. Such organisms might reproduce in radically different ways, metabolize in novel fashions, and adapt to their environments through mechanisms inconceivable to terrestrial biologists. While largely speculative, these concepts illuminate the vast landscape of potential life forms across the cosmos and urge us to broaden the scope of our exploratory frameworks. Some life forms may exist that, on first encounter, we might not recognize as alive, challenging our definitions of biology itself. In a parallel Earth where multicellular life never emerged, the planet would present an extraordinary tableau of microbial dominance. Oceans and continents would teem with single-celled organisms, each perfectly adapted to its niche. From the crushing depths of ocean trenches to windswept mountain peaks, microbes would rule every ecosystem. Without the oxygenation surge driven by photosynthetic plants and algae, atmospheric composition would remain closer to primordial conditions, with oxygen levels far lower than today. The chemical landscape of such a world would differ profoundly, affecting sky color, surface reactions, and the potential for certain chemical cycles. No forests, no grasslands, no coral reefs, only sprawling microbial mats creating textures and colors visible from orbit, forming landscapes both alien and mesmerizing. Without multicellular organisms, intelligent life would never arise, leaving the world unobserved and its evolutionary theater a mystery, known only to the simplest forms of life. Atmospheric composition is a primary architect of life's trajectory. On Titan, where methane dominates, life forms could evolve unique respiratory systems to metabolize hydrocarbons. Membranes or organs could specialize in extracting energy from methane molecules, creating creatures entirely unlike anything on Earth. In contrast, carbon dioxide-rich atmospheres might fuel expansive plant life or plant-like organisms whose advanced photosynthetic abilities could support diverse herbivorous species, driving complex ecosystems. Thin or unprotected atmospheres might favor smaller, radiation-resistant life forms with reflective skins, protective shells, or subterranean habitats to avoid harmful ultraviolet rays. Across planets, life adapts to chemical, radiative, and thermal constraints, giving rise to forms perfectly suited to their environments, yet profoundly different from terrestrial norms. Genetic coding systems further shape the scope of life. The DNA code, translating nucleotide sequences into proteins, underpins all known biology. Were this code more intricate, life could produce a far greater variety of proteins, enabling specialized and resilient organisms capable of surviving extreme conditions or exhibiting unprecedented abilities. A simpler code might limit protein diversity, favoring streamlined life forms, efficient in certain contexts, but less adaptable overall, reducing evolutionary complexity and the potential for advanced life. The current balance, 4 nucleotide bases forming 20 amino acids, strikes a delicate equilibrium, fostering the staggering diversity of organisms that populate Earth today, from microscopic bacteria to towering trees and highly sophisticated animals. Ultimately, the interplay between light, atmosphere, biochemistry, and genetics frames the possibilities for life both on Earth and across the cosmos. By imagining worlds with radically different conditions and life forms, we open a window into the endless variations evolution could produce. stretching the boundaries of our understanding of biology and the universe itself. From the tiniest bacteria invisible to the naked eye to the vast complexity of multicellular organisms like humans, life across universes with altered physical laws or constants could manifest in ways that stretch the imagination. In a cosmos where nuclear fusion ignites at much lower temperatures than our sun, entire ecosystems might derive energy not from starlight, but from the ambient fusion reactions suffusing their environment. Life forms in such a universe could literally feed on the heat of subatomic collisions, converting energy directly from the processes that drive the cosmos itself. In a universe dominated by stronger electromagnetic forces, organisms might evolve to draw energy from magnetic fields, electrical currents, or even the plasma flows of planetary atmospheres, thriving in environments that would be lethal in our reality, such as the violent, swirling storms of gas giants. Universes where dark energy behaves differently could unlock exotic energy sources previously unimaginable. Here, life might tap directly into the fabric of space-time, drawing power from quantum fluctuations or the stretching of space itself. Such beings could appear less as material organisms and more as ripples or disturbances in the energy fields of their universe, defying conventional ideas of matter. In worlds with extraspatial dimensions, life could exploit gravitational potentials or the complex interplay of higher dimensional forces, moving between planes or drawing power from forces entirely alien to human understanding. Every cosmos presents its own canvas, its own palette of physical laws, shaping the forms and strategies life might evolve to survive. Symbiosis, the intimate cooperation between species, could dominate evolutionary processes to an extraordinary degree. Organisms might evolve as inseparable composite entities, much like lichens on Earth, which combine fungi and algae. Entire ecosystems could be interwoven webs of mutual dependence, where survival hinges not on competition, but on collaboration. These composite life forms could fuse the strengths of multiple species, becoming extraordinarily adaptable, resilient, and capable of thriving across environments that would challenge single-species life. Boundaries between organisms could blur, producing ecosystems where traits and abilities are shared and exchanged through symbiotic relationships, accelerating evolution and creating highly specialized and multifunctional organs. Plants with sensory faculties rivaling animals or animals with photosynthetic skin might become commonplace, their physiology shaped by a deep interdependence forged over millennia. Gravity would sculpt life in fundamental ways. On planets with weaker gravity than Earth, organisms could grow taller, more slender, and more delicate. Trees might tower with minimal support, animals could develop long, graceful limbs, and flight might become possible for species that would be earthbound in stronger gravitational fields. In worlds of intense gravity, life would adapt through compact, sturdy forms. Plants would grow thick, powerful stems to withstand the pull, and animals would evolve dense skeletons and muscular bodies to resist constant downward force. Internal processes would also respond. Blood flow, respiratory efficiency, and cardiac output could shift dramatically to meet the demands of gravitational extremes. Across entire ecosystems, gravity would dictate species distribution, forest canopies, and even the architecture of coral reefs, revealing the profound interconnection between physical forces and life's evolution. Humans themselves might have evolved along radically different paths. If our ancestors had been different creatures entirely, upright bipedalism might not define us. We could move on all fours, swing through canopies, or possess specialized limbs for climbing, burrowing, or manipulating the environment in unique ways. Sensory perception could be unrecognizable. Echolocation like bats, infrared vision like snakes, or entirely new senses tuned to magnetic or electrical fields could dominate our experience of reality. Our brains might have evolved to prioritize different cognitive faculties, reshaping language, abstract thought, and problem solving, and fundamentally altering society. Civilization, technology, and culture would reflect the abilities and needs of these alternate humans, creating histories and civilizations unimaginable to us. In some universes, intelligence itself could defy conventional bounds. Quantum effects might dominate macroscopic cognition, allowing decision-making based on probabilities or simultaneous possibilities rather than linear logic. Intelligence could be distributed throughout the body, producing collective or hive mind structures in which individual consciousness contributes to a larger network. In worlds dominated by extreme environmental forces, human-like intelligence might manipulate electromagnetic fields directly, achieving what could appear as telekinesis or telepathy. Human perception could expand far beyond the traditional five senses. Magnetoreception could allow precise navigation across planets, while the ability to perceive ultraviolet or infrared light could reveal patterns and heat signatures invisible to ordinary eyes. The most transformative senses might allow direct interaction with subatomic particles, unveiling the quantum nature of the world around us and unlocking scientific insights currently beyond our reach. Every object, every process would be seen in a radically new light, reshaping our understanding of reality itself. Human physiology demonstrates remarkable adaptability. At high altitudes, bodies produce more red blood cells and optimize lung function to extract oxygen from thin air. In extreme heat, sweating efficiency and blood flow adjust to dissipate excess warmth. Across time and circumstance, the human body reveals an astonishing capacity to evolve and acclimate, reflecting a universal principle. Life in all its forms is defined by its ability to adapt, harness energy, and find niches in the vast array of physical realities the cosmos can provide. Conversely, in the harshest, coldest environments, the human body orchestrates a remarkable ballet of adaptation to survive. Metabolic rates accelerate, generating more internal heat, while blood circulation to fingers, toes, and other extremities increases to stave off the creeping threat of frostbite. Every shiver, every pulse becomes a calculated response, a testament to the body's ability to maintain life in the face of extreme temperatures. Yet, the challenges humans face are not limited to Earth's climate. In the weightless expanse of space, astronauts encounter a completely different set of trials. Microgravity erodes bone density and diminishes muscle mass, yet the cardiovascular system adjusts with stunning efficiency, circulating blood without relying on gravity's pull. Re-entry to Earth's environment can be jarring, with bones and muscles needing to readjust, but these changes underscore the body's extraordinary capacity for adaptation, reshaping itself to survive in conditions far removed from its evolutionary origin. Human lifespan, a fundamental measure of existence, carries implications that ripple through society, culture, and our very understanding of the universe. Imagine if humans could live for several centuries. Long-term space missions, once constrained by the ticking clock of mortality, could become viable ventures spanning generations, allowing explorers to traverse vast cosmic distances. Scientists might devote decades, even centuries, to unraveling the mysteries of the universe, accelerating our comprehension of celestial phenomena at a pace previously unimaginable. Conversely, if human life were drastically shorter, urgency would dominate every action. Knowledge would need to be transferred rapidly between generations. Space exploration would prioritize immediate results, and scientific innovation might surge in intensity, fueled by the pressing need to achieve meaningful breakthroughs before time runs out. Longer lives could foster meticulous, measured progress, refining technologies and understanding over centuries, whereas shorter lives could ignite bursts of daring experimentation and rapid advancement, each generation racing to leave its mark. Our perception of time, the universe, and our role within it would be irrevocably altered. Extended lifespans might cultivate reverence for the slow unfolding of cosmic phenomena, while fleeting lives could magnify the incomprehensibility of space's vastness, reshaping humanity's relationship with the cosmos itself. As technological prowess expands and humans extend their reach beyond Earth, social structures are poised for profound transformation. Traditional nation-states might dissolve, replaced by decentralized global networks organized around shared knowledge, expertise, or ideology, rather than geography. Space colonization could foster governance systems unlike any seen on Earth, adapted to isolated habitats, orbital stations, or distant planetary surfaces. Cultures would evolve in response to unique environments, diverging sharply from Earthbound norms over time. Advanced artificial intelligence and instantaneous communication networks might revolutionize democracy, allowing real-time participation in policymaking and reducing reliance on conventional representative structures. The potential for increased human longevity would enable multi-generational planning, cultivating governance that prioritizes sustainability, legacy, and the long-term survival of societies across decades, even centuries. Human reproduction, a cornerstone of biology shaped over millions of years, has vast societal and evolutionary consequences. Were humans to reproduce via parthenogenesis, females could generate offspring independently, eliminating the need for male genetic contribution. Family structures, romantic partnerships, and societal constructs would undergo seismic shifts, while genetic diversity might decline, heightening vulnerability to disease and environmental change. Alternatively, if humans were sequential hermaphrodites capable of changing sex throughout life, society could experience unprecedented empathy between genders, transforming parenting, careers, and social hierarchies. Such scenarios underscore the deep interconnection between reproductive biology and societal organization, revealing how altering one aspect of human life cascades across culture, relationships, and identity. In parallel universes, communication could manifest in forms utterly alien to our own. Aquatic humans might rely on bioluminescent signaling, flashing intricate patterns of light to convey emotion and thought. Others could develop telepathy, sharing ideas instantaneously, rendering verbal speech obsolete, but redefining privacy and social boundaries. Multiple-limbed humans might craft a multidimensional sign language, expressing complex ideas simultaneously, while those in extreme environments could communicate via infrasound over vast distances, reshaping societal structure and interpersonal bonds. Human cognition, too, could vary dramatically across realities. Some might possess instantaneous mathematical computation, others heightened spatial reasoning or perfect memory, while some could wield amplified empathy. Societies built on such diverse cognitive abilities would assign roles based on mental strengths, yet coordination and understanding could present unprecedented challenges, redefining collaboration and human interaction. Emotions, fundamental to human experience, could differ radically under alternative physical laws. In a universe where time flows nonlinearly, feelings might intertwine past, present, and future, creating emotional states far beyond current comprehension. Additional spatial dimensions could tie emotions to geometric configurations, producing reactions unrecognizable to us. Changes in fundamental particles or forces could produce entirely new emotional experiences, or even eliminate emotions as we understand them, replacing them with alien forms of perception and response. Imagine a world devoid of electricity, where human ingenuity turns to alternative energy sources. Bioluminescence could illuminate cities, the glow of engineered bacteria replacing street lamps. Gravitational energy might power urban landscapes through controlled weight descent, while piezoelectric technology could transform roads and clothing into sources of electrical power, charging devices as humans move through daily life. Communication could rely on light or compressed air, transportation could harness antimatter reactions, and society would evolve in directions scarcely imaginable from our current perspective. Human resilience, creativity, and adaptability would be stretched to their limits, producing a civilization uniquely tailored to its environment, technological constraints, and biological possibilities. From frostbitten extremities to the boundless reaches of space, from centuries-spanning lifetimes to radically different reproductive, cognitive, and communicative possibilities, human existence is defined not only by its current constraints, but by its limitless potential to adapt, imagine, and transform across the infinite tapestry of time, space, and possibility. In a parallel universe, computing might unfold along paths both astonishing and unexpected. Imagine a reality where silicon-based transistors never dominated the landscape of technology. Instead, organic compounds form the very foundation of computational systems, growing and evolving with the fluidity of living organisms. In this world, computers could adapt seamlessly to new problems, reshaping themselves according to the demands of their environments. Quantum computing is not a niche pursuit, but the default mode of operation. From handheld devices to sprawling data centers, every system taps into quantum superposition and entanglement, enabling calculations so complex that what would take today's most powerful supercomputers millennia could be solved in mere seconds. Central processing units, as we know them, may have never existed. Computation is distributed across networks of specialized nodes, each handling specific tasks with precision. This architecture fosters resilience, self-repair, and continuous optimization, producing a computational ecosystem that thrives autonomously. Human-computer interfaces transcend screens and keyboards. Direct neural connections allow users to manipulate data and programs through thought alone. This fusion of human cognition and artificial systems blurs the boundary between organic and digital intelligence, creating a hybrid form of creativity and problem-solving previously unimaginable. In this reality, artificial intelligence evolves along a radically different trajectory. Organic computing dominates, with scientists cultivating networks of living neurons capable of processing information like a brain, yet operating on scales far beyond human cognition. These biological AIs perceive the world through engineered sensory organs, sensing phenomena beyond our comprehension. At the cellular level, they exploit quantum effects to calculate and resolve problems with precision that surpasses any mechanical system. Their perception of reality and consciousness mirrors living beings more than machines. Ethical frameworks expand, confronting us with questions of rights and responsibilities for these sentient computational entities. Interaction with such organic intelligence is symbiotic, challenging conventional notions of life, intelligence, and the essence of consciousness. The path of AI development is shown to be not predetermined, with each choice in research shaping alternate realities with profound consequences for humanity and the universe itself. Transportation technologies in other universes evolve in ways dictated by the governing physical laws. In realms with stronger gravity, levitation may be impossible, giving rise to tunneling systems or vehicles constructed from ultra-dense materials. In low-gravity worlds, flying transport is commonplace, and native life forms may evolve natural flight. Variations in atomic structure could allow materials that enable teleportation or instantaneous matter transfer, rendering traditional movement obsolete. In universes where time flows differently, transportation might focus on temporal displacement rather than physical motion, with vehicles engineered to traverse streams of time. Some realms possess extra-spatial dimensions, enabling shortcuts through unseen paths where vehicles vanish from one point and reappear at another. Exotic energy structures might allow propulsion through dark energy or unknown forces, fundamentally altering the concept of distance. In certain universes, consciousness could traverse space without moving matter, challenging the very need for transport. These differences produce transportation technologies that defy our imagination, tailored to the unique physics of their worlds. In a universe where the space race followed a different trajectory, Mars becomes the primary target rather than the Moon. By the late 1970s, permanent research stations flourish on the Red Planet, staffed by rotating international crews studying Martian geology and seeking evidence of ancient microbial life. This alternate approach accelerates the development of sustainable off-world habitats and closed-loop life support systems, paving the way for asteroid mining in the 21st century. Orbital factories exploit microgravity to manufacture materials impossible on Earth. Humanity establishes a stronger foothold in space, sending robotic probes to the icy moons of Jupiter and Saturn to explore subsurface oceans for life. This alternate timeline fosters international cooperation, inspiring generations to pursue science and engineering, driving technological advancement and expanding humanity's presence in the cosmos. Energy production in parallel universes also diverges dramatically. In universes with stronger nuclear forces, fusion occurs naturally, enabling compact stellar-like energy systems and microfusion reactors that surpass today's power capabilities. In worlds with weaker electromagnetic forces, conventional electricity generation is insufficient, leading civilizations to harness gravitational energy through tidal forces or even extract power from spinning black holes. Additional spatial dimensions provide new avenues for energy extraction, creating possibilities that appear fantastical from a three-dimensional perspective. Variations in particle physics allow exotic matter to serve as energy sources. In a universe abundant with antimatter, industrial-scale matter-antimatter annihilation produces nearly limitless energy. Biotechnology in these universes evolves in extraordinary directions, shaped by principles beyond our current understanding of DNA and genetics. Life itself may serve as both computational medium and energy source, blending biology, technology, and physics into a seamless continuum. In these worlds, every aspect of existence, from intelligence to movement to energy, is reimagined, revealing a cosmos where the laws of nature themselves dictate astonishingly different forms of life, technology, and civilization. However, if evolution had taken a different trajectory, the tapestry of life and technology we inhabit today could look almost unrecognizable. Envision a world where humanity's scientific curiosity did not turn first to genetic manipulation, but instead to the intricate microscopic realms of microorganisms and their symbiotic partnerships. In this alternate reality, entire industries might revolve around microbial alchemy, with fermentation transcending its culinary roots to produce a staggering variety of new materials, medicines, and biochemicals. Cities could be alive in a literal sense, dominated by towering bioreactors filled with engineered algae, converting carbon dioxide into clean energy and oxygen, their gentle luminescence pulsing like a living organism as they sustain urban life. Architecture in such a world might borrow directly from nature's own ingenuity. Buildings would grow, repair themselves, and adapt fluidly to seasonal shifts and environmental stressors, mimicking the resilience and efficiency of trees, coral reefs, or termite mounds. Clothing would no longer be a static layer. Instead, it could breathe and respond dynamically to our body heat, purify the surrounding air, or even provide protective functions against pollutants and pathogens. Medicine, instead of manipulating genes directly, might revolve around the human microbiome. Personalized microbial therapies could enhance mental acuity, strengthen immunity, and extend human longevity, rendering chronic disease a relic of the past. This alternate path of biotechnology is a testament to the boundless creativity of life and science, highlighting that the journey of innovation is neither linear nor predetermined. Across the cosmos, the very notion of communication could diverge wildly in different universes, shaped by the unique physical laws of each reality. Imagine a universe with more pliable space-time, where messages traverse vast distances instantly by warping the fabric of reality itself. In another, particles or forces unknown to our physics might permit thought to flow through a cosmic lattice, rendering telepathy commonplace, instantaneous, and deeply intertwined with daily life. In realms with unusual electromagnetic properties, communication might rely on exotic waves imperceptible to our senses, or in a universe attuned to gravity waves, entire civilizations could converse via ripples in space itself. In yet other realities, entanglement might operate on macroscopic scales, allowing instant information transfer regardless of distance, fundamentally reshaping the concept of interaction. In some universes, time might flow in nonlinear patterns, or consciousness could span multiple planes simultaneously, turning the very act of communication into something almost unrecognizable to our human intuition. Nanotechnology, too, could follow alternative principles beyond our current comprehension. Rather than manipulating matter at the molecular level, nanomachines in these worlds might harness quantum entanglement to act across immeasurable distances, coordinating seamlessly in ways that defy classical physics. Such devices could phase through solid objects, exist in multiple states simultaneously, or draw energy directly from the quantum vacuum, removing any need for conventional power. Their collective behavior could manifest intelligence far beyond contemporary artificial intelligence, forming shape-shifting structures capable of instant adaptation to environmental shifts or human commands. The implications of such technology would be profound, blurring the line between the micro and macro, enabling feats that today exist only in the realm of science fiction. From molecular assemblers capable of constructing anything atom by atom to miniature wormhole generators for instantaneous travel or communication. Medical science across these alternate realities could develop in wildly divergent directions. Some universes might perfect genetic engineering, eradicating disease before it emerges and cultivating organs tailored to each patient, eliminating the need for donors. Elsewhere, nanobots could patrol the bloodstream tirelessly, repairing tissue damage, reversing aging, and extending lifespans beyond our current imagination. Other worlds might merge artificial intelligence with human biology seamlessly, with neural implants augmenting cognition and AI systems diagnosing and treating illness with precision and speed. In still other realities, psychic healing or energy-based therapies could become scientifically validated and mainstream, allowing the mind itself to manipulate the body's physiology, achieving what would seem magical to us. The story of Earth itself might have been written differently if mass extinctions had not punctuated its history. These catastrophic events, devastating as they were, cleared the stage for evolutionary innovation. The end Permian extinction, known as the Great Dying, annihilated over 90% of marine species and most terrestrial life. Its survivors radiated into empty ecological niches, setting the stage for the rise of dinosaurs, creatures that might never have dominated if prior life forms had persisted. Similarly, the extinction event that extinguished the dinosaurs opened the door for mammals to diversify into the vast array of forms we recognize today, ultimately giving rise to humans. Without these cataclysms, the intricate, intertwined web of life on our planet and our place within it might have followed a profoundly different story, one unrecognizable to the eyes of our current imagination. The absence of dinosaurs created a vast, open stage for mammals to explore territories and roles previously denied to them, gradually leading to the emergence of primates and eventually culminating in the rise of humans, our own species. Without these dramatic resets in Earth's evolutionary history, life might have followed entirely different trajectories, shaping a world unrecognizable to us today. Ecosystems as we know them, with their intricate interdependencies, varied species, and ecological niches, might never have formed. Instead, the planet could still be dominated by ancient reptilian lineages, limiting biodiversity and constraining the emergence of entirely new forms of life. Without the invention of agriculture, human civilization would have evolved along a markedly different path. Small, nomadic hunter-gatherer bands would have persisted as the prevailing social structure, populations scattered across landscapes, constantly on the move in pursuit of migrating herds and seasonal plant growth. Large, permanent settlements, reliant on consistent food supplies, would have been rare if they existed at all. Instead, humans would have honed extraordinary skills in tracking, hunting, and foraging, developing intimate, multi-generational knowledge of the flora, fauna, and environmental rhythms of their regions. Tools would have become increasingly sophisticated, specialized for hunting, fishing, and food processing, while innovations in clothing, shelter, and transportation would adapt to the demands of a nomadic existence. Social organization in such a world would have looked very different. Communities would remain small and relatively egalitarian, with minimal hierarchies. Land ownership might not have emerged as a concept, and cooperative resource sharing would be vital for survival. This alternate path would produce a human species less capable of large-scale environmental alteration, slower technological advancement, yet remarkably attuned to the natural world, thriving through adaptation and ingenuity rather than domination. Throughout human history, empires have risen and fallen, reshaping the world in profound ways. Imagine, however, if these trajectories had diverged. If the Mongol Empire had not fragmented but continued its relentless expansion, Eurasia might have been unified under a single political and economic system, its vast trade networks accelerating cultural exchange and technological innovation far beyond what history records. If the Chinese Ming dynasty had maintained naval supremacy, its treasure fleets could have established colonies across the Indian Ocean, Africa, and perhaps even the Americas, spreading Chinese influence and dramatically shifting the global balance of power. Consider, too, a world where the Aztec or Inca empires had successfully resisted European conquest. Over generations, they might have developed immunity to Old World diseases, acquired advanced weaponry, and emerged as global powers capable of rivaling European nations. Colonization patterns, global culture, and technological development would have diverged entirely, producing a world map and social landscape nearly unrecognizable to us. Language, religion, governance, and trade networks would all reflect this alternative history, highlighting the fragile contingency of human progress and the immense complexity of factors shaping civilizations. The Industrial Revolution, which transformed human society in just a few centuries, was itself fueled largely by coal and other fossil fuels, unleashing rapid technological innovation, urbanization, and industrial-scale production. Without this concentrated energy source, the pace of technological and societal transformation might have been far slower, and the modern world, with its sprawling cities, global economies, and mechanized industries, might not have emerged in its present form. Human history, then, is a delicate weave of ecological shifts, social innovations, and fortuitous events. The extinction of ancient species, the rise of agriculture, the expansion and contraction of empires, and the discovery of concentrated energy sources all intertwine, creating the rich, complex tapestry of our present world. Every alternative scenario, whether involving species, civilizations, or technology, offers a window into a world both familiar and alien, reminding us that the path we tread was never predetermined, but rather the outcome of countless intersecting forces across time and space. However, if alternative sources of energy had been accessible and widely implemented during the critical phases of industrial expansion, the trajectory of human history might have been utterly transformed. The windswept plains and rushing rivers already served as rudimentary power sources, yet their potential remained vastly underutilized. Imagine a world where advanced windmills, more efficient than their historical counterparts, harness the relentless gusts to drive massive factories, while intricately designed water wheels transformed river currents into unstoppable engines of production. Coal would no longer dominate, and the choking smog that once enveloped industrial cities might have been replaced by crisp, clear air, changing not only public health, but the very pace at which human societies impacted the climate. Solar energy, though primitive at the time, could have benefited from early investment, with experimental collectors powering small workshops and expanding gradually into larger industrial applications. Geothermal energy, tapping the Earth's hidden heat, might have redefined where industries thrived, concentrating innovation in regions previously overlooked. Entire urban landscapes and economies would have shifted, forming a network of sustainable industrial hubs with profound global implications for politics, trade, and culture. And if humanity had set its gaze toward the stars centuries earlier, our understanding of both technology and ourselves would have evolved in leaps unimaginable. Space exploration, undertaken long before the 20th century, could have accelerated technological progress at a staggering pace. Early encounters with the challenges of extraterrestrial survival would have fueled breakthroughs in physics, engineering, and material science, propelling humanity into an era of advanced computing, powerful propulsion systems, and artificial intelligence far ahead of our historical timeline. Our perception of Earth, fragile and interconnected, might have taken root generations earlier, prompting proactive stewardship of our planet, shaping environmental consciousness centuries before the modern ecological movement. The political and cultural ramifications would have been equally dramatic. Without a Cold War space race, humanity might have embraced prolonged eras of international collaboration in space, reshaping diplomacy, art, and philosophy through a lens of interstellar exploration. Literature and creative thought could have reflected a universe of possibility, instilling a global ethos of curiosity, innovation, and shared destiny. Across parallel realities, religious and philosophical landscapes could have unfolded in ways both subtle and radical. One universe might see ancient Egyptian polytheism ascend as the dominant global faith, with worshippers venerating deities like Ra and Osiris into the modern era. Another could witness the rise of a scientifically informed atheism, where spiritual practices emphasize mindfulness and personal development rather than supernatural belief. In yet another, Buddhism might dominate regions historically tied to Christianity or Islam, embedding principles of karma and reincarnation into governance, education, and daily routines. Entirely new faiths might emerge from alternate historical pressures. Religions built around extraterrestrial contact, environmental stewardship, or cosmic consciousness, each uniquely sculpting societies in unforeseen ways. Pandemics, too, act as forces capable of reshaping civilization. Consider the Black Death, sweeping through Europe in the 14th century. If it had been less catastrophic, feudal hierarchies might have persisted longer, delaying the cultural and economic shifts that culminated in the Renaissance and the Industrial Revolution. Conversely, a more virulent Spanish flu in 1918 could have radically altered the outcome of World War I, rewriting borders, treaties, and the geopolitical landscape of the 20th century. The early containment of the AIDS epidemic, or a hastened development of an effective vaccine, might have saved millions of lives, profoundly influencing demographic trends, economic development, and political power structures, particularly in Africa. The outcomes of pandemics intertwine with medical knowledge, public health infrastructure, and societal responsiveness. Alternate scenarios would not merely affect mortality, but could redirect the evolution of medical research, international cooperation, and even human immune resilience, leaving ripples across science, politics, and human development. Economic systems, if designed differently, could have rewritten the fabric of societies. A resource-based economy, distributing goods according to need rather than profit, might have curtailed poverty and fostered unprecedented equity, while a circular economy emphasizing reuse, recycling, and waste reduction could have nurtured innovation in materials science, and sustainability, embedding environmental consciousness into the core of industrial activity. Worker-owned cooperative models could have democratized workplaces, reduced income disparities, and cultivated strong communal ties within organizations, fundamentally transforming social and economic interactions. Each alternative path, whether in energy, exploration, health, or economics, sketches a reality that challenges the familiar narrative of history, hinting at a world where human ingenuity, curiosity, and foresight could have reshaped civilization in ways still tantalizingly within reach. Lastly, envision a society where the flow of resources is not dictated by money, but by voluntary gift-giving, where exchanges occur out of goodwill rather than obligation. Such a gift economy, though immensely challenging to scale, has the potential to reshape social dynamics in profound ways. Communities could become tightly knit, with trust and reciprocity forming the foundation of everyday interactions. Individual wealth accumulation would no longer dominate priorities, allowing cooperative and collective well-being to flourish. Beyond economics, these alternative systems could fundamentally alter societal values, the structure of labor, and the allocation of resources, creating ripple effects that touch every facet of human development and social progress. Now, consider the sequence of scientific discoveries as a delicate choreography that shapes our understanding of reality. Had pivotal breakthroughs occurred in a different order, our perception of the universe, technology, and ourselves might look entirely alien. Imagine Einstein revealing the theories of relativity before Newton had formulated classical mechanics. Physics would have developed along a path we can barely conceive, our notions of space, time, and motion fundamentally altered. Similarly, if the double helix of DNA had been unraveled before the theory of evolution took hold, humanity could have leapt forward in genetics and medicine decades or even centuries earlier. Think of quantum mechanics emerging before classical physics had been fully understood. We might have approached nature from the subatomic level first, perhaps advancing nanotechnology, quantum computing, and molecular engineering long before we ever fully grasped macroscopic mechanics. The ordering of discovery has tangible consequences. If nuclear fission had been harnessed prior to the steam engine, the Industrial Revolution could have unfolded in a radically different manner, with energy, manufacturing, and transportation systems taking forms almost unimaginable today. The geopolitical landscape, shaped by the distribution of technological power, would also have diverged along a startlingly different trajectory. Astronomy, too, is guided by the sequence of revelation. If exoplanets had been detected before we fully understood our own solar system, the quest for other worlds and extraterrestrial life might have begun with a very different perspective, influencing our sense of cosmic identity. Scientific breakthroughs do more than inform. They sculpt the very lens through which we interpret the universe and our role within it. Across parallel universes, the patterns of human migration could vary as drastically as the landscapes themselves. Picture a world where continents never drifted apart, forming a single massive supercontinent. Humans might have dispersed evenly, cultural diversity emerging in ways alien to our historical experience. In another universe, prolonged, extreme ice ages could have confined populations near the equator for millennia, creating dense settlements and sophisticated civilizations in tropical regions while delaying the colonization of colder climates. In yet another scenario, early humans mastering advanced seafaring technologies thousands of years earlier could have spread across oceans far sooner. Island nations might rise as dominant centers of culture and power, while continental interiors remain sparsely populated, reshaping trade, conflict, and innovation. These alternative migration patterns would not just influence where humans live, but how societies interact with the environment, develop technology, structure governance, and even physically adapt to their habitats. Earth's continental arrangement is a silent architect of life itself. Shifting land masses would alter climate, ocean currents, and ecosystems in ways that ripple across evolutionary and human history. Imagine a planet with a vast equatorial continent where moisture is trapped near the coasts, creating enormous deserts inland. Ocean currents, the planet's heat conveyors, would twist into unfamiliar patterns, producing regions of unprecedented warmth or cold. The Gulf Stream might vanish, Europe's climate shifting dramatically. Flora and fauna would evolve under new constraints. Isolated lands like Australia could become unparalleled evolutionary laboratories, while vast connected continents might allow species to spread widely, paradoxically reducing biodiversity. Human civilization tightly intertwined with geography would be unrecognizable. Atmospheric composition also wields tremendous influence over climate and habitability. Earth's nitrogen-oxygen mix interacts with solar radiation and planetary rotation to produce the weather we know. But a methane-rich atmosphere like that of Saturn's moon Titan could generate storms, rainfall, and seas in wholly alien forms. Denser atmospheres might spawn storms of titanic proportions, raging for centuries, visible from space as colossal, swirling maelstroms of gas, a constant reminder of nature's raw, untamed power. In all these possibilities, from human societies to the stars above, the sequence of events, the layout of land, the makeup of air, and the generosity of human systems together form a tapestry of infinite variation, each thread capable of producing worlds both familiar and utterly alien, shaping life, knowledge, and civilization in ways we are only beginning to imagine. Conversely, on a planet cloaked in a thin, fragile atmosphere, the dance of weather becomes subtle yet volatile, a delicate choreography governed by extremes. Day and night would impose drastic temperature swings, with the sun scorching the surface by day and plunging it into near-freezing cold by night. This relentless cycle of heating and cooling would force the air to expand and contract rapidly, triggering sudden localized tempests, whirling dust devils, and flashes of turbulent windstorms that sweep unpredictably across barren landscapes. The composition of the atmosphere itself holds immense sway over these patterns. For example, a world saturated with carbon dioxide could trap heat with remarkable efficiency, plunging it into a runaway greenhouse state where surface temperatures climb to extraordinary heights. Under such conditions, rain could be transformed into corrosive acid, or even molten metal might fall from the sky if the planet is sufficiently hot for metals to exist as gaseous vapors, creating weather phenomena almost unimaginable to an earthbound observer. These alien atmospheres craft climates and storms far beyond human experience, each planet offering a singular testament to the universe's astonishing diversity. Imagine vegetation that defies our familiar green. Leaves might shimmer in shades of deep purple, blazing red, or even pitch black, if plants evolved to harness light differently. The pigments within leaves capture sunlight for photosynthesis, and while chlorophyll dominates on Earth, alternative pigments would absorb different wavelengths, casting landscapes in colors both breathtaking and alien. A plant using pigments that reflect violet and absorb red light would cloak entire forests in a haunting purple glow. Such transformations would ripple through ecosystems. Growth rates and species distribution would shift, altering the delicate balance between herbivores and predators. The reflectivity of the planet's surface, or albedo, would change, subtly modifying weather and climate on a global scale. Life has already shown its adaptability. Certain algae and bacteria in Earth's oceans use unique pigments to survive in dim, green-depleted depths. The potential for vibrant, unconventional photosynthesis elsewhere hints at ecosystems whose rules challenge our most fundamental assumptions about life. Volcanic activity shapes worlds with a dramatic, almost sculptural hand. On Earth, volcanoes create towering mountains, flowing lava plains, and jagged cliffs, leaving indelible marks on the landscape. Beyond our planet, their impact grows even more extreme. Mars hosts Olympus Mons, a shield volcano nearly 3 times the height of Mount Everest, a monument to volcanic endurance and planetary transformation. Venus presents a molten panorama. Hundreds of volcanoes and sprawling lava plains hint at a history of relentless eruptions. Its thick, superheated atmosphere, a lingering signature of greenhouse gases released over eons. Even Mercury and our moon bear the faint traces of volcanic pasts, ancient lava flows etched among impact-cratered surfaces, whispering of smaller-scale geologic tumult long since subdued. Volcanoes, in essence, are architects of planetary identity, reshaping surfaces and atmospheres alike. Imagine rivers defying the very pull of gravity, flowing uphill across a world with altered gravitational fields. In this inverted hydrology, valleys might be dry, while mountaintops collect cascading streams. Watersheds are redefined, ecosystems reinvented. Aquatic life could evolve mechanisms to navigate against conventional flows, while terrestrial creatures develop intimate relationships with these highland reservoirs. Weather patterns would rearrange entirely, clouds forming and raining in unexpected locales, fostering a surreal yet functional environmental rhythm. Gravity, usually an invisible constant, would instead orchestrate a planet-wide ballet of water, life, and climate. Evolution, unbounded and inventive, could sculpt life into unimaginable forms. On a low-gravity world, creatures might drift through the air, bodies gossamer thin, wings or tendrils catching the wind like living kites. Extremes in temperature could foster beings able to transition between liquid and solid states, braving freezing nights and searing days with chemical metamorphoses. In storm-ridden, electrically charged atmospheres, organisms might generate bioelectricity, navigating and communicating with currents drawn from the air itself. In worlds starved of light, life could exploit geothermal energy or chemical reactions, glowing with bioluminescence that replaces sight itself, sensing the environment through heat, vibration, or electromagnetic cues. Life need not resemble anything we know. Colonies of interdependent individuals, creatures capable of manipulating elemental forces, or sentient organisms thriving under alien physics. Evolution's canvas stretches across possibilities as vast and unpredictable as the cosmos itself. Now, look to the skies. On a world with differing atmospheric chemistry, the familiar blue dome above could shift into shades of amber, orange, green, or deep violet. Saturn's moon Titan offers a real glimpse into this alien vision. Thick hydrocarbon haze paints the sky in muted orange, an eerie, otherworldly twilight. A planet dense with chlorine gas might appear pale green, an environment perhaps hostile to human life but striking in its visual poetry. Even minor changes, more particles, altered gas concentrations, could deepen, lighten, or shift sky colors, influencing not only aesthetics but life itself. Photosynthesis, animal navigation, and behavioral patterns could all adapt to these atmospheric variations, making the sky a silent narrator of planetary character. Finally, cosmic radiation sculpts worlds on a more invisible scale. High-energy particles streaming from distant stars and galaxies bombard planetary surfaces, altering atmospheres, breaking molecular bonds, and stripping away lighter elements over millennia. Planets lacking protective magnetic fields are particularly vulnerable, their surfaces and atmospheres continuously sculpted by this relentless cosmic influence. Radiation can hinder the emergence of life, shape chemical pathways, and gradually erase the subtle atmospheric signatures that define a world, reminding us that planetary environments are fragile tapestries woven from forces both visible and unseen. The universe is a theater of extremes, a place where atmospheres, light, gravity, chemistry, and cosmic energy combine to craft environments of stunning diversity. Every planet tells a story, every storm, color, and organism revealing the remarkable potential of nature's boundless creativity. Conversely, planets endowed with powerful magnetic fields, much like Earth, enjoy a remarkable defense against the relentless bombardment of cosmic radiation. These invisible magnetic shields bend and redirect charged particles hurtling through space, forming a protective cocoon that surrounds the entire planet. This invisible fortress is not just a defensive measure. It is essential for preserving a stable atmosphere and safeguarding every form of life from the ceaseless assault of high-energy radiation. Paradoxically, moderate exposure to cosmic radiation can have subtle yet profound effects on planetary environments. It catalyzes chemical reactions high in the atmosphere, crafting complex molecules that could serve as the raw ingredients for life itself. Some theorists propose that cosmic radiation may have been instrumental in Earth's earliest chapters, promoting genetic mutations and diversification in primitive life forms, ultimately shaping the evolutionary trajectory that led to the complex biosphere we witness today. Imagine a world in which Earth's geological heartbeat pulsed at an entirely different rhythm. If tectonic and volcanic forces accelerated dramatically, the planet would transform into a theater of ceaseless upheaval. Mountains would erupt and crumble within mere decades, continents would drift apart at a pace observable to the naked eye, and volcanoes would spew molten rock in near constant fury. Year after year, familiar landscapes would vanish, replaced by chaotic terrains, rendering long-term human settlements almost impossible. Conversely, if the geological tempo slowed to a near standstill, Earth would appear frozen in time. Tremors might occur once every 1,000 years, and the birth of new mountain ranges could stretch across billions of years. Such lethargic processes would profoundly influence life on Earth, reducing the environmental pressures that drive adaptation, diversity, and evolution. The speed of geological processes is intimately connected to the planet's carbon cycle and climate stability. Rapid rock weathering could strip the atmosphere of carbon dioxide too quickly, risking an icy global freeze, while sluggish cycles might allow greenhouse gases to accumulate unchecked, triggering runaway warming. Our comprehension of Earth's past and its potential future hinges on the delicate balance maintained by these slow-moving forces. From the recycling of the crust to the distribution of life-essential minerals, the world we know is an intricate product of this measured geological tempo. Beyond the familiar phenomena of rain and snow, Earth's cosmic neighbors present a bewildering array of precipitation types that reshape landscapes in alien ways. On Venus, sulfuric acid rain descends from thick, oppressive clouds, but vaporizes before touching the blistering surface. Over millennia, this corrosive drizzle etches dramatic patterns into highland terrains, sculpting a world of stark and otherworldly beauty. Titan, Saturn's largest moon, witnesses methane rain filling vast lakes and carving icy riverbeds. This liquid methane, interacting with the organic compounds scattered across its surface, sculpts channels, coastlines, and expansive dune fields in forms reminiscent of Earth, yet composed entirely of alien materials. Farther afield, Neptune may host an even more exotic spectacle: diamond rain. Deep within its crushing interior, carbon atoms are compressed into precious crystals that plunge toward the core, influencing internal structure and the planet's magnetic field. Each form of precipitation, from acid to hydrocarbons to gemstones, underscores the staggering diversity of weather systems beyond our home planet, leaving their indelible marks upon the cosmic stage. Earth's evolutionary narrative could have diverged spectacularly if human-like intelligence had never emerged. Absent our ancestors' unique blend of reasoning, tool use, and social cooperation, other creatures might have seized dominance. Imagine dinosaurs persisting through the epochs, evolving greater cognitive faculties, with species like velociraptors developing complex societies and environmental mastery. Alternatively, intelligent mammals, perhaps dolphins or whales, might have risen to global prominence. Envision sprawling underwater metropolises, a civilization orchestrated through sonar and bioluminescent signaling, thriving in oceans that cover much of the planet. These aquatic societies would have engineered architecture adapted to extreme pressures, harnessed ocean currents and thermal vents for energy, and devised intricate transportation systems, blending biological evolution with technological ingenuity. Consider a universe dominated not by individual beings, but by a colossal hive mind. In such a collective consciousness, the notion of individuality dissolves, replaced by unified decision-making and shared perception. Every thought, action, and innovation emerges from a vast network, potentially spanning entire planets or star systems. Tasks are distributed efficiently across the collective, while information flows instantaneously, eliminating traditional communication barriers. Yet, such cohesion carries its own limitations. Creativity often thrives in the friction of individual perspective, and a species functioning as a single entity may struggle to produce the novel ideas that ignite evolutionary leaps. In contemplating these alternative realities, from accelerated tectonics to alien precipitation, from aquatic civilizations to hive-mind intelligences, we glimpse the astonishing variability of life, matter, and consciousness. Each scenario emphasizes the delicate interplay of cosmic forces, planetary rhythms, and evolutionary potential that combine to produce the worlds, creatures, and minds that populate the universe. The Earth we inhabit is but one outcome of countless possibilities, a fragile equilibrium poised between chaos and order, stability and transformation, familiar and utterly alien. Additionally, the species could be extremely susceptible to systemic threats, as an attack on a single part of the collective might jeopardize the entire organism. The existence of such a life form would profoundly transform the development of the universe, compelling a complete reevaluation of consciousness, society, and the very essence of intelligent life. Adapting to extreme temperatures presents formidable challenges for civilizations, yet human ingenuity has produced a wide array of strategies to confront these harsh environments. In searingly hot regions, underground living spaces act as natural air conditioners, shielding inhabitants from relentless heat. Cities such as Kuba Pedy in Australia have perfected this method, with residents carving homes into hillsides to escape the blistering desert sun. These subterranean dwellings maintain a stable, comfortable temperature throughout the year, providing relief from extremes. Conversely, in icy environments, insulation becomes a critical necessity. Traditional Arctic communities have long relied on animal furs and ingeniously constructed igloos to conserve heat. Modern engineering has expanded on these ancient principles, introducing advanced insulation materials and heating systems capable of withstanding temperatures that plummet to minus 80 degrees Celsius in places like Antarctica. Research stations there rely on thick walls, carefully calibrated ventilation, and energy-efficient heating to sustain life in an environment that is otherwise inhospitable. Water management also plays a pivotal role in survival under extreme conditions. In arid regions, civilizations have developed elaborate irrigation networks and water storage methods. The ancient city of Petra, for example, thrived amidst the desert through a sophisticated system of aqueducts and cisterns. In frigid regions, preventing water from freezing in pipes and maintaining a continuous supply requires constant monitoring and specialized engineering. Energy production and conservation are similarly vital. Solar energy is highly effective in hot, sun-drenched areas, while wind turbines may be more practical in colder climates. Efficient energy use is crucial across all environments to maintain livable conditions. Looking toward the future, these adaptive strategies will become increasingly critical as climate change alters global temperature patterns. Imagine a universe where multiple intelligent species coexist and thrive in harmony. This scenario, though currently beyond our direct experience, unlocks extraordinary possibilities for interstellar collaboration and shared advancement. Different species might contribute distinct skills and insights, propelling scientific discovery and cultural exchange to unprecedented levels. One species could master abstract mathematics, while another excels in engineering, and together their combined knowledge might yield technological breakthroughs unimaginable for any single species. Interspecies diplomacy would reach remarkable sophistication, developing complex communication systems that incorporate multiple sensory modalities to bridge biological differences. This could produce a rich, multi-layered form of galactic discourse, cultivating profound understanding and empathy across species boundaries. Cooperative efforts among diverse intelligent beings could generate solutions for cosmic scale challenges, such as interstellar travel or the long-term survival of civilizations. Pooling knowledge and resources, these species could unravel universal mysteries at an extraordinary pace, ushering in an era of unprecedented cosmic exploration and discovery. Civilizations evolving in low-gravity environments would encounter distinctive challenges and opportunities that would shape their development in extraordinary ways. Reduced gravitational pull would profoundly affect physiology, architecture, and technology. Inhabitants of low-gravity worlds might evolve taller, more slender physiques, with diminished bone density and muscle mass over generations, resulting in elongated limbs and more fragile skeletal structures. Architecture would adapt dramatically, allowing for towering structures requiring minimal support, creating sprawling vertical cities impossible on Earth. Transportation might emphasize aerial or magnetic levitation systems as conventional ground-based vehicles become inefficient. Technology priorities would shift accordingly, with space exploration and off-world colonization progressing more rapidly due to reduced energy demands for escape from weak gravity. Yet, Earth-dependent technologies might struggle, necessitating innovative solutions for daily tasks, including cooking, waste management, and fluid handling. Imagine a civilization whose technological evolution diverged from silicon and metal, embracing the intricate complexity of living systems. In such a world, computers might be grown rather than assembled, with information processed through neural networks reminiscent of biological brains. These organic devices could self-repair and upgrade, adapting to new challenges like living organisms evolving over time. Energy might be harvested from engineered plants capable of capturing and storing sunlight far more efficiently than contemporary photovoltaic cells. Transportation could involve specially bred creatures or living vehicles with muscles and nerves replacing engines and circuits. These biological machines would be self-repairing, fueled organically, and capable of regenerating damaged parts. Medicine could advance through symbiotic microorganisms residing in the human body, continuously monitoring health and preventing or treating illnesses. A biological approach to technology would foster a sustainable symbiotic relationship with the environment, transforming civilization into an ecosystem of living technologies. The distinction between natural and artificial would blur as creations become increasingly lifelike and human understanding of living systems deepens. In such an advanced civilization, energy harnessing would be multifaceted, combining solar, biological, geothermal, and other sources to sustain society, ensuring adaptability and resilience in an ever-changing universe. One of the most abundant and readily accessible sources of power for any civilization would be solar energy, capturing the radiant, relentless output of their star with immense arrays of photovoltaic panels or solar thermal collectors. These vast installations could blanket planetary surfaces, covering deserts, plains, and mountains with shimmering sheets of energy-harvesting material, or they could orbit the planet, suspended in space to intercept unfiltered starlight around the clock, harnessing energy with maximum efficiency. Beyond solar power, wind and hydroelectric energy could be employed to tap into the natural kinetic forces coursing through a planet's atmosphere and water systems. Gigantic wind farms stretching for hundreds of miles could capture the ceaseless flow of air currents, while enormous hydroelectric dams would transform the motion of rivers, waterfalls, and tides into vast reserves of usable electricity. Geothermal energy would dig even deeper, literally tapping into the planet's molten core to access a steady, reliable heat source. On tectonically active worlds, geothermal plants could provide constant energy day and night, storm or shine, unaffected by surface conditions. For civilizations requiring concentrated high-output energy, nuclear fission and fusion might become the backbone of their infrastructure. Fission, the splitting of heavy atomic nuclei, releases enormous amounts of power, while fusion, the joining of light atomic nuclei, has the potential to produce near-limitless energy with minimal waste. Mastery of fusion could revolutionize a civilization, allowing them to power entire cities, terraform planets, or even support interstellar travel. Pushing the boundaries even further, antimatter reactions would represent a staggering leap in energy potential, releasing energy orders of magnitude greater than chemical or nuclear reactions, though producing and containing antimatter presents monumental technical challenges. Civilizations operating at the peak of engineering might even construct megastructures, such as Dyson spheres or swarms, to capture the total energy output of their star. Such constructs would dwarf any planetary-scale energy system, supplying energy sufficient for interstellar exploration, planetary engineering, or even altering the orbits and climates of worlds within their system. Exploring the possibilities of non-carbon-based intelligent life expands the imagination even further. While all known life is carbon-based, scientists speculate that entirely different biochemistries could give rise to complex, intelligent organisms. Silicon, for example, has chemical properties capable of forming long chains and intricate molecules, suggesting the possibility of silicon-based life in high-temperature environments or on worlds with thick, volatile atmospheres. Similarly, life could be based on nitrogen and phosphorus chemistry, thriving in ammonia-rich oceans or on frozen, distant moons like Titan orbiting Saturn. Such beings, if they evolved intelligence, would likely experience the universe in ways incomprehensible to humans. Their perceptions, senses, communication methods, and even the structure of their societies could diverge radically from anything on Earth, highlighting the extraordinary diversity that life could take across the cosmos. Interstellar communication presents a monumental challenge, especially for civilizations seeking methods beyond conventional electromagnetic waves. One possibility is the use of neutrino beams. Neutrinos, nearly massless particles that barely interact with matter, can traverse entire galaxies without being absorbed, allowing communication over unimaginable distances. Advanced civilizations might develop technologies capable of generating and detecting precisely targeted neutrino streams. Another method could involve the manipulation of gravitational waves, ripples in the fabric of space-time, first predicted by Einstein and now detected by humans, as a medium for transmitting information across cosmic scales. Quantum entanglement offers another tantalizing avenue. This phenomenon links particles instantaneously regardless of distance, and while current understanding suggests it cannot transmit information faster than light, a highly advanced civilization might harness its potential in ways humanity cannot yet conceive. Other possibilities include the use of exotic particles or the direct manipulation of space-time itself, opening doors to communication methods entirely beyond present human physics. Imagine a world without money. Without currency, all economic interactions would be transformed. Bartering and direct trade would replace coins and bills, requiring people to offer goods, services, or skills that others desired, making every transaction a negotiation in its purest form. Wealth accumulation would take on an entirely different meaning, reliant on stored resources or rare skills, rather than bank accounts. Long-distance commerce would be severely limited, as transporting vast quantities of goods would be cumbersome. Societies would likely become decentralized, with communities organized around local resources and mutual cooperation rather than centralized governments. Debt might be reframed as promises of labor or reciprocal favors, fundamentally reshaping notions of obligation. Innovation could slow without financial incentives, yet collaboration and shared knowledge might flourish as individuals focus on mutual survival and prosperity. An energy-based economy would transform these dynamics further. Instead of trading dollars or euros, people could trade units of energy, kilowatt hours, joules, or other measures, creating a system where wealth directly corresponds to energy production, conservation, and consumption. Solar farms, wind turbines, and hydroelectric plants might become the mints of such a civilization, while individuals and businesses would be driven to optimize energy efficiency, as wasted energy would equate to lost wealth. Goods and services would carry explicit energy costs for production, transport, and usage, shaping consumption patterns and incentivizing technological innovation to reduce energy expenditure. Jobs could be evaluated based on energy output or savings, directly linking productivity to societal reward, while reframing how societies value work. Envision a world where every individual has equal access to food, water, energy, and resources. Extreme poverty would vanish, and wealth inequality would collapse. Everyone would have their basic needs met: nourishing food, safe shelter, reliable healthcare, and sufficient energy for daily life. Such a world would prioritize balance and sustainability, aligning human activity with environmental constraints and fostering a culture of shared responsibility and collective well-being. This vision, combining advanced energy technologies, alternative life forms, innovative communication methods, and equitable resource distribution, paints a universe of possibilities both astonishing in scale and rich in diversity, where civilizations harness unimaginable power, explore the cosmos, and redefine the very foundations of existence itself. However, this idealized vision would inevitably confront a labyrinth of profound challenges. The practical realities of redistributing wealth and resources on a global scale are staggering in complexity. Entire economic systems, long entrenched and finely tuned to serve a fraction of the population, would need to be dismantled and reconstructed from the ground up. Those who currently hold a disproportionate share of resources would likely resist with formidable force, both politically and economically. The question of innovation and growth looms large in this scenario. Some argue that the drive to accumulate wealth fuels technological breakthroughs and entrepreneurial endeavors, and without such incentives, the pace of progress could slow markedly. Yet, the flip side suggests that if the basic needs of all people were met, countless individuals would gain the opportunity to pursue education, creative endeavors, and scientific research, potentially accelerating cultural and technological advancements in ways currently unimaginable. Environmental considerations would demand equally rigorous attention. If every individual consumed resources at the levels typical of high-income countries, the planet would face unsustainable stress, pushing ecosystems beyond recovery. Striking a balance between equitable resource distribution and ecological sustainability would be not only necessary but urgent, requiring careful planning and innovative environmental management. While the concept of absolute equality in resource distribution remains largely theoretical, it forces reflection on pathways toward a more fair and sustainable civilization. In a world without scarcity, the very foundations of economics would be transformed. Such a society would rely on advanced technologies capable of producing near-limitless energy and materials, achievements potentially realized through fusion power, molecular replication, or nanotechnology. Once scarcity is removed from the equation, the economic focus would shift from rationing limited goods to managing abundant ones. Citizens could gain unfettered access to necessities and luxuries alike without relying on traditional monetary systems. Freed from the need to work merely for survival, individuals could devote their energies to pursuits of personal interest, communal benefit, or intellectual curiosity. Innovation would thrive on intrinsic motivation, the pursuit of knowledge, or the satisfaction derived from problem solving. Collaboration could replace competition as the dominant societal model, since the incentives to hoard resources or knowledge would vanish. Yet, even in a world of material abundance, certain forms of scarcity would persist. Time, unique experiences, and rare or irreplaceable items would retain intrinsic value, fostering a new economy based on access and fairness rather than survival. As knowledge becomes the primary economic driver, societal structures and values would undergo a profound transformation. Intellectual capital would eclipse physical assets in determining wealth and influence, reshaping our perceptions of success. Education and research would become the engines of economic growth, with nations and corporations heavily investing in human potential. Universities, think tanks, and research institutes would emerge as the true centers of power, supplanting traditional industrial hubs. The most influential companies would be those capable of generating, processing, and disseminating knowledge rather than manufacturing tangible products. Innovation would accelerate at an unprecedented pace as the free flow of ideas becomes the lifeblood of progress. Collaborative platforms and open source initiatives would flourish, dissolving disciplinary boundaries and promoting the cross-pollination of knowledge. Fields such as artificial intelligence, biotechnology, and space exploration would advance at extraordinary rates. However, this shift would introduce new challenges. The digital divide could deepen, leaving those without access to information even further behind. Intellectual property law would grow increasingly complex, requiring novel frameworks to balance fair compensation with the rapid circulation of ideas. Moreover, the very nature of work would evolve, demanding continuous adaptation and learning to remain relevant in a society driven by constant discovery. An economy centered on biological resources, often termed a bioeconomy, would further reshape humanity's interaction with the natural world. In this system, renewable plant-based materials would replace finite fossil resources as the backbone of industry. Agriculture, forestry, and marine ecosystems would provide raw materials for a vast range of products, from everyday packaging and textiles to advanced pharmaceuticals and biofuels. A bioeconomy offers profound sustainability advantages, as biological resources can regenerate within human timeframes when managed responsibly. This transformation could drastically reduce greenhouse gas emissions and mitigate environmental degradation, creating a harmonious balance between economic activity and planetary health. In such a future, humanity's relationship with the Earth, technology, and knowledge would be fundamentally redefined. Societies could shift from a struggle for survival to a pursuit of collective progress, where curiosity, creativity, and cooperation replace competition and scarcity as the driving forces of civilization. However, transitioning to a bioeconomy would not be a simple shift. It would demand monumental transformations across nearly every aspect of society. Entire infrastructures would need to be redesigned, technological innovations would have to be implemented on a global scale, and societal habits would require deep reconsideration. The delicate balance between harnessing biological resources for energy, materials, and industrial use, while ensuring sufficient food production and the preservation of natural ecosystems, would become a central challenge. Any misstep could trigger cascading consequences such as widespread deforestation, soil degradation, or dramatic losses in biodiversity. Yet, if executed thoughtfully, a bioeconomy could chart a path toward a future where human development and economic growth are no longer at odds with ecological sustainability. Imagine cities powered entirely by renewable organic sources, transportation networks fueled by algae-derived biofuels, and industries built on biodegradable materials, all operating in harmony with the rhythms of nature. Imagine a world where the standard currency is not money at all, but time itself. A system in which every person is allocated a finite time budget, perhaps linked to average life expectancy. In this world, purchasing a luxury item could cost years of your life, while a simple meal might subtract only a few hours. Every transaction becomes a literal exchange of the most precious and non-renewable resource, life itself. This direct relationship between consumption and lifespan would force humanity to reevaluate priorities, making every choice profoundly consequential. In a strange way, this mirrors our current system, where we trade hours of labor for money and then use that money to acquire goods and services. By eliminating the middle step, this hypothetical time-based economy creates an unmediated link between existence and material consumption, highlighting the true cost of every desire and impulse. Questions of fairness and equity arise naturally. Would everyone start with the same allotment of time? How would differences in health, lifestyle, and longevity be accounted for? These considerations underscore the complexity of value and exchange, revealing that even abstract constructs like money are merely proxies for our finite temporal existence. In a society where property rights no longer exist, the foundational assumptions of economics would be upended. Rather than individual ownership, resources and goods would exist as communal assets, managed collectively for the benefit of the entire community. This vision resembles a large-scale sharing economy in which access is prioritized over possession. Social organization might center around principles of mutual aid, with individuals contributing their labor and skills toward communal objectives. Allocation of goods and resources could be determined democratically or by councils tasked with ensuring fairness and sufficiency. Production and distribution would prioritize meeting basic needs over profit maximization, while incentives for work and innovation might arise from social recognition or a sense of collective responsibility rather than personal gain. However, efficiently distributing resources and motivating productivity in such a system would present profound challenges, necessitating a radical reconception of trade, investment, and economic growth. While such a society could reduce inequality and enhance sustainability, it would require a fundamental reorientation of values, governance structures, and the very way humans relate to one another and to their environment. The complete replacement of human labor by automation would trigger another profound societal upheaval, reshaping work, income, and the rhythms of daily life. Traditional jobs might vanish entirely as machines and artificial intelligence take over tasks ranging from industrial manufacturing and transportation to complex decision-making and creative problem-solving. Economic models built around wage labor would be rendered obsolete, demanding new approaches such as universal basic income to ensure equitable access to resources. Taxation systems, government roles, and financial structures would need to be reinvented to accommodate a world where income is decoupled from employment. Socially and psychologically, humans would face the challenge of redefining purpose and identity in the absence of work as a central organizing principle. Freed from the constraints of obligatory labor, societies could experience a renaissance of creativity, intellectual exploration, and artistic endeavor, as individuals redirect their energies toward personal passions, collaborative projects, and scientific discovery. In a diverse ecosystem populated by multiple intelligent species, trade and economic interaction could evolve in extraordinary ways. Each species would bring unique resources, abilities, and needs to the table, establishing natural pathways for mutually advantageous exchanges. An aquatic species might provide rare minerals harvested from deep ocean trenches in exchange for technological innovations or agricultural products produced by terrestrial beings. Communication across species would require innovative solutions, possibly through universal translators or shared symbolic languages, and could give rise to interspecies marketplaces or hubs where commerce is conducted collectively. The goods and services exchanged might range from tangible materials to specialized labor, cognitive abilities, or cultural artifacts. As interseas trade networks expand, the creation of financial systems, formal agreements, and collaborative ventures could foster cooperation, understanding, and stability across the ecosystem, intertwining the fates of diverse life forms in ways previously unimaginable. Music itself could undergo a radical transformation if tonal perception were no longer bound to the scales and intervals humans currently recognize. Consider systems in which dozens or even hundreds of pitches exist within a single octave, or where entirely new mathematical relationships define harmony. Microtones, already used in certain Eastern musical traditions, could expand to create entirely alien chord progressions, reshaping emotional responses to sound. Consonance and dissonance might be redefined, influencing both musical education and instrument design. The very experience of listening could become a form of cognitive exploration, requiring the mind to adapt to structures unlike anything in contemporary culture. Music could become not merely an auditory pleasure, but a portal into alternative ways of understanding pattern, emotion, and structure. If human vision could perceive a broader spectrum of electromagnetic radiation, the artistic landscape would transform in ways previously unimaginable. Artists would wield ultraviolet, infrared, X-ray, and radio wave colors, crafting works that shift depending on temperature, position, or energy exposure. Paintings might reveal hidden details under ultraviolet light. Sculptures could appear to morph when viewed in infrared, and radio wave installations might allow audiences to perceive entirely new forms of spatial expression. This expanded visual palette would inspire unprecedented creativity, introducing new mediums, techniques, and perspectives. Art could engage with hidden realities, alternate dimensions, and the invisible forces that shape our universe, offering not just aesthetic pleasure, but profound insight into the unseen fabric of existence. In every case, these scenarios challenge our understanding of value, labor, creativity, and perception. They illustrate that even concepts as familiar as currency, property, work, sound, and vision are deeply contingent, and that imagining alternatives can open pathways to entirely new ways of living, interacting, and understanding the universe. Furthermore, this expanded vision of perception could utterly transform the way humanity experiences and interprets historical artworks. Paintings and sculptures that have existed for centuries might suddenly unveil hidden textures, subtle brushstrokes, or underlying sketches when observed through varied wavelengths of light. Each layer revealed could offer unprecedented insight into the techniques, materials, and even the thought processes of artists long past. Art historians might uncover nuances in color blending or composition that were invisible to the naked eye, and the very narrative of art history could be rewritten as these invisible details come to light. Imagine a world where a painting is no longer a static object, but a dynamic puzzle, with each element whispering fragments of untold stories, and each viewer discovering a slightly different truth depending on how they observe it. Similarly, literature might evolve in parallel, discarding the constraints of linear narrative to become a labyrinthine experience of ideas, moments, and emotions. Readers could wander through works where time does not march forward but folds upon itself, presenting events in a kaleidoscope of interconnected vignettes. Stories would no longer rely on a chronological sequence, but instead offer a rich tapestry of impressions, a network of incidents and revelations where the meaning emerges through exploration rather than instruction. Authors might focus less on plot and more on the depth of immersion, allowing characters, themes, and emotions to interweave freely. Each reader's engagement would be uniquely personal, as the order of discovery could reshape the story itself. The boundaries between poetry, prose, and visual storytelling might dissolve, giving rise to hybrid literary forms that challenge conventions and push the limits of language. Readers could interact with text like a living ecosystem, discovering hidden patterns, resonances, and echoes that speak differently to each mind. In parallel, dance and movement would experience astonishing transformations under altered gravitational conditions. On planets with lighter gravity than Earth, dancers could soar to incredible heights, their leaps extending into long, elegant arcs, and spins multiplying effortlessly as inertia becomes easier to overcome. Movements previously impossible on Earth could become commonplace, creating airborne choreographies that seem to defy physics. Conversely, in high-gravity environments, dance would emphasize strength, control, and fluidity under pressure. Every motion would be deliberate, with grounded techniques emphasizing resilience and endurance. Movements might evolve into wave-like undulations that harmonize with a heavier pull rather than fight against it. In microgravity, such as aboard orbiting space stations, dance could become fully three-dimensional, liberating performers from the constraints of up and down. Dancers could float, twist, and propel themselves in intricate formations, turning the surrounding space into a canvas. Props, costumes, and choreography would evolve to match these new physical realities. Ribbons and lightweight materials in low gravity, supportive gear in high gravity, and tethers or handholds in microgravity to control motion while maintaining elegance. Imagine, too, a universe where telepathy is the dominant medium for artistic expression. Artists could transmit their thoughts, emotions, and visions directly into the minds of their audience, eliminating the need for conventional tools. Viewers would experience the creative process as a living, breathing event, sensing the artist's intention, energy, and subtleties in real time. Music, visual art, poetry, and even abstract concepts could merge into single, multi-layered transmissions, blurring the boundaries between mediums. Yet, such intimacy would bring challenges. The ethics of consent, privacy, and mental boundaries would become central, requiring both artists and audiences to develop unprecedented awareness and control. Society could shift dramatically with heightened empathy and understanding as direct communication becomes normal, affecting not just the arts but education, therapy, diplomacy, and conflict resolution. The culinary arts, too, would be transformed as humanity spreads into extraterrestrial environments. On Mars, hydroponic crops adapted to the planet's extreme conditions could develop intense flavors and unique textures, requiring chefs to invent entirely new techniques. In microgravity environments, such as space stations, chefs might engineer foams, emulsions, and other creations that maintain form despite zero gravity, while water scarcity could inspire revolutionary waterless cooking methods using electromagnetic fields or other advanced technologies. Exotic ingredients from extreme Earth environments, radiation-tolerant fungi, deep-sea algae, or extremophile organisms could become culinary staples, enriching the diet of spacefarers with proteins, nutrients, and tastes previously unknown. Synthetic biology could allow chefs to grow organisms that produce exact flavors, textures, or nutrient compositions, enabling the creation of foods entirely alien to our current experience. Meals could become sensory adventures, carefully crafted to adapt to the environment, physiology, and even psychological needs of the diners, transforming sustenance into an art form that integrates science, creativity, and imagination in ways we have only just begun to imagine. Human perception, artistic expression, movement, and nourishment might all evolve together, creating a world where the familiar laws of time, space, and gravity no longer dictate experience. Art, literature, dance, telepathy, and cuisine could merge into multidimensional experiences, each medium influencing and amplifying the others. The universe itself could become a stage for human creativity, a laboratory for endless experimentation where imagination, science, and sensory exploration intersect in astonishing, previously unimaginable ways. And imagine a world where architecture no longer clings rigidly to the ground, where every structure pulses with adaptability and movement, reshaping itself in response to the rhythms of human life and the caprices of the environment. Streets could be lined with buildings that breathe, expand, and contract as if alive, homes stretching their walls during daylight hours to maximize living areas, only to fold inward at night, conserving energy while creating intimate, efficient spaces. Office towers could transform in real time, corridors shifting, walls sliding, and floors rotating to accommodate fluctuating workforces or team projects, creating dynamic interiors that reflect the ebb and flow of modern labor. The distinction between vehicle and dwelling would blur. Houses might detach from their foundations, gliding silently across landscapes, offering people the rare freedom of relocating without leaving their home behind. Skyscrapers could boast rotating floors, sections sliding outward to sculpt ever-changing skylines that dance with sunlight and shadow, turning the urban panorama into a living, kinetic artwork. In regions vulnerable to natural disasters, architecture could adopt a protective choreography, folding into secure shapes or breaking into modular, resilient units in response to earthquakes or hurricanes, creating safety without surrendering form. Schools and community centers might metamorphose fluidly. During 1 hour, they are performance theaters, in another, sports arenas, and when calamity strikes, emergency shelters equipped to sustain life. Such a vision demands materials capable of bending the rules of physics, engineering that marries imagination with precision, and energy systems both intelligent and self-sustaining. This is architecture that questions permanence, place, and the very notion of how we inhabit space, promising cities of unprecedented flexibility, resilience, and environmental harmony. And fashion, too, would evolve under these extremes, prioritizing function with astonishing ingenuity. On planets scorched by relentless ultraviolet rays, clothing might employ reactive materials that shift color to signal harmful exposure, integrated with nanotechnology that self-repairs, maintaining protective integrity over decades of wear. In microgravity, garments would become modular, effortlessly accommodating bodily shifts, with magnetic fasteners replacing zippers and expandable fabrics adjusting to fluid movement, ensuring efficiency and freedom of motion. Underwater colonies might favor attire embedded with breathing aids, pressure regulators, and bioluminescent patterns, glowing softly to facilitate communication while camouflaging seamlessly with the deep ocean's inky darkness. In freezing wastelands, clothing could harness advanced heating systems and adaptive fabrics, drawing energy from motion, sunlight, or wind, sculpting warmth and mobility into sleek, intelligent designs that negate bulk while amplifying endurance. Fashion would become survival, art and technology intertwined, transforming the human body into a living interface capable of thriving across the most hostile environments imaginable. And imagine art itself dissolving the boundary between reality and imagination, where performance transcends canvas and stage to manipulate perception itself. Artists might harness advanced technologies or theoretical physics to bend space and time, creating immersive experiences that defy the ordinary laws of nature. A single performance could link distant locations through quantum entanglement, allowing participants to exist simultaneously in multiple realms, or distort matter to form ephemeral landscapes that vanish at the blink of an eye. Spectators would navigate realities crafted not only by human intention, but by the pliability of physics itself, glimpsing alternate dimensions, exploring consciousness through tangible, interactive phenomena. This fusion of science and art could ripple outward, informing psychology, physics, and philosophy, while raising profound ethical questions. When reality itself becomes a medium, who governs its limits, and what responsibilities accompany such creative power? And in societies with perfect memory, culture transforms into a living mosaic of unbroken historical fidelity. Stories, rituals, and traditions remain immutable across generations, their details preserved in crystalline clarity. Oral histories retain their richness, myths and legends resonate with original intent, and even the smallest nuances of ancient customs persist, creating a society saturated with the depth of its past. Yet perfect recall challenges adaptation. Cultural evolution slows as deviations are remembered and corrected. Traditions ossify around their original contexts, resisting the fluidity of change that imperfect memory once allowed. New practices may arise not from creativity alone, but from the management of memory itself. Rituals to navigate the collective mind, ceremonies to revisit and reinterpret the endless layers of preserved history, sophisticated systems for cataloging and accessing shared recollections becoming central cultural pillars. And in the cosmos, the tantalizing idea of parallel universes beckons. Some scientists speculate that the gravitational influence of unseen worlds may ripple across our own, leaving subtle imprints in cosmic radiation, while others hypothesize entangled particles bridging realities, a hidden dialogue of quantum states stretching across dimensions. Galaxies may bear the faint signatures of external universes, cosmic inflation patterns hinting at interactions beyond our perception, and particle colliders might one day glimpse micro-black holes, small doorways into multiversal landscapes. Communication with these alternate realities could harness gravitational waves or exploit intersections in higher dimensions, yet such possibilities carry immense risk, destabilizing the very fabric of space, inviting unknown matter or energy into our universe, and confronting humanity with alternate selves or conflicting histories, each collision a challenge to identity, perception, and society itself. And as all these visions converge, architecture that moves, clothing that adapts, art that manipulates reality, memory that never fades, and universes that might converse, they sketch a future where imagination, technology, and existence are inseparable, where humans inhabit not only space and time, but the malleable boundaries between possibility and reality, forever redefining what it means to live, perceive, and create. Furthermore, we must confront the profound ethical implications of venturing into the realms of other universes. Every action we take in such a context carries consequences that could ripple across realities in ways that are difficult, if not impossible, to predict. The idea that our interventions might inadvertently cause harm, collapse structures, or even annihilate entire worlds stretches our moral imagination to its limits. This sobering possibility underscores the necessity of extreme caution, meticulous planning, and an unparalleled depth of understanding before any endeavor to interact with parallel universes could even be contemplated. The concept of exchanging information, energy, or matter across universes pushes the boundaries of contemporary physics and challenges the limits of human comprehension. While firmly in the theoretical domain, scientists have speculated on several extraordinary mechanisms that could make such exchanges conceivable. Quantum entanglement, for example, describes the mysterious connection between particles across vast distances, a phenomenon Albert Einstein famously dubbed spooky action at a distance. Some theorists posit that entanglement could, in principle, bridge separate universes, offering a conduit for the transfer of information across otherwise impenetrable cosmic boundaries. Equally compelling is the theory of cosmic inflation, which suggests that the universe underwent a rapid, exponential expansion in its earliest moments. Certain cosmologists have proposed that this process might generate countless bubble universes, each expanding within a grander multiversal structure. Occasionally, these bubbles might collide or interact, creating fleeting opportunities for energy, or perhaps even matter, to traverse between universes. The notion of wormholes introduces yet another speculative pathway. These hypothetical tunnels through the fabric of space-time might, if they exist, connect distant regions of our universe or potentially link entirely separate universes, offering a theoretical gateway for inter-universal exchange. Yet, the scientific possibilities are only one facet of this vast dilemma. The ethical questions surrounding contact with parallel universes are staggering. We would have to grapple with the fundamental issue of interference. If intelligent life exists in these alternate realities, would our presence or communication disrupt their natural evolution, social structures, or technological trajectories? Even actions rooted in benevolent intentions might have catastrophic unintended consequences, destabilizing ecosystems, societies, or civilizations in ways we cannot foresee. The potential for cultural contamination is immense. Sharing knowledge or technology might irrevocably alter the beliefs, values, and development of an entire intelligent species. Furthermore, the question of authority and representation arises. Who would have the moral or political right to act on behalf of our universe? How could humanity establish protocols for diplomacy with entities whose biology, psychology, or even concept of existence might be utterly alien? Entire new frameworks for interuniversal relations would need to be conceived, far surpassing the sophistication of current international diplomacy. Philosophically, the stakes are equally profound. Confirmation of parallel universes would force humanity to reconsider notions of free will, destiny, and the fundamental nature of reality itself. Ethical responsibility in this context extends beyond human society to encompass the fates of entire alternate worlds. On a more scientific plane, the existence of parallel universes invites radical reconsideration of the laws of physics. Each universe might operate under distinct sets of fundamental constants. Gravity could be weaker or stronger, altering the formation of stars, planets, and galaxies. Stellar lifespans might vary dramatically, with some universes experiencing stars that burn out in a few million years, while others sustain their suns for durations incomprehensible to us. Causality itself could take on new meaning. Events in one universe might influence or be influenced by occurrences in another, challenging our foundational understanding of cause and effect and opening the door to paradoxes or entirely new physical paradigms. Moreover, interactions between universes could shed light on the enigmatic nature of dark matter and dark energy. These unseen components of our cosmos, which remain among the greatest mysteries in astrophysics, might be explained, or at least partially influenced, by forces or entities originating beyond our universe. Each hypothetical interaction could provide fresh avenues for research, sparking a revolution in cosmology, particle physics, and the theoretical frameworks that underpin our understanding of reality. Despite these tantalizing possibilities, the notion of traveling between parallel universes remains, for now, the province of speculative physics and science fiction. The ethical dilemmas, scientific challenges, and philosophical questions it evokes are immense, demanding a level of foresight, restraint, and intellectual rigor that humanity has rarely had to muster. Yet the sheer scope of these ideas, the potential to connect with worlds beyond our own, to encounter realities governed by radically different laws of nature, and to confront the moral weight of such interactions, invites contemplation on a scale that is as humbling as it is exhilarating. However, scientists have long speculated about technologies that, if parallel universes truly exist, might one day allow us to traverse the boundaries separating them. Among the most captivating of these ideas is the concept of traversable wormholes. These hypothetical tunnels, twisting through the very fabric of space and time, could act as bridges linking distant regions of our universe, or even entirely separate universes. The creation and stabilization of such a wormhole would demand matter with negative energy density, a strange, exotic substance that defies the conventional laws of physics as we currently understand them. The very idea challenges our notions of what is physically possible, pushing the boundaries of imagination and scientific theory. Another speculative avenue lies in the manipulation of higher dimensions. According to string theory, our universe may be threaded with additional spatial dimensions beyond the three we perceive. If these hidden dimensions exist, they might offer pathways through which one could move into parallel universes, stepping into realms where the familiar laws of physics could operate differently. The implications are staggering, suggesting that what we consider insurmountable barriers of space might actually be navigable with the right knowledge and technology. Quantum entanglement adds yet another layer of possibility. This phenomenon links particles in ways that defy ordinary understanding. A change to one particle instantaneously affects another, regardless of distance. While we are far from harnessing entanglement to transport macroscopic objects, theorists imagine a future where the quantum threads connecting particles across universes could be used as bridges, enabling the travel or communication between realities. Such an achievement would demand advances not only in technology, but in our fundamental comprehension of the quantum world. Encountering our parallel selves introduces profound philosophical and psychological implications. The many worlds interpretation of quantum mechanics suggests that every conceivable outcome of every choice spawns a new universe. In these alternate realms, different versions of ourselves have made divergent decisions, creating lives that might vary in astonishing ways. Meeting these alternate selves would challenge our understanding of identity and individuality. We might confront versions of ourselves who pursued entirely different careers, formed different relationships, or adhered to contrasting beliefs. The experience could force a reckoning with the role of chance, choice, and circumstance in shaping who we are. It might illuminate the intricate web of determinism and free will, revealing how decisions, no matter how small, ripple across the cosmos in ways that are both subtle and profound. This encounter would also reshape our perception of personal identity, by transforming it from a fixed entity into a spectrum of possibilities. Recognizing that multiple iterations of ourselves exist in parallel realities could cultivate empathy, encouraging a deeper understanding of the capacity for growth and change in ourselves and others. Our lives, once seen as a singular narrative, would become threads in a vast cosmic tapestry, interwoven with countless alternate versions. Imagine a multiverse in which parallel universes exist at various stages of development. Some might be in their infancy, filled with primordial gases yet to coalesce into stars. Others could be flourishing, their galaxies spinning with complex life, civilizations emerging and exploring. Still others might be entering decline, stars dimming, black holes dominating, a slow march toward entropy. Each universe follows its own distinct timeline, creating a patchwork of cosmic evolution. In one universe, the first stars might just be igniting. In another, advanced civilizations could be probing the farthest reaches of space. The pace of cosmic expansion could vary, shaping the formation of galaxies and stars in ways unimaginable in our own universe. Physical laws themselves might differ. Gravity could be stronger in one realm, dark energy more dominant in another, altering the very structure and destiny of each cosmos. The concept of universes at differing stages of evolution raises tantalizing questions about the potential for interaction. Could these realms influence one another? Are the principles governing their development universal or uniquely tailored to each cosmic arena? As we explore the farthest reaches of our own universe, the possibility of parallel realities adds a layer of awe and wonder, expanding the scope of what we consider possible. Interacting with parallel universes would fundamentally alter our understanding of reality. The linear, singular perception of existence would give way to a vast, interconnected web of possibilities. Communicating with or observing alternate versions of our universe could illuminate how small divergences lead to radically different outcomes, emphasizing the weight of every decision. We might glimpse worlds where history unfolded in entirely new ways. Civilizations rose or fell under different circumstances, or the basic laws of physics themselves took alternate forms. Such revelations would deepen our grasp of possibility, probability, and the astonishing complexity of existence itself, inviting us to reconsider not only where we are, but who we are across the infinite expanse of the multiverse. Moreover, contact with parallel universes could unlock solutions to problems that have long confounded humanity within our own reality. Imagine discovering technologies or scientific breakthroughs that have already been achieved in alternate universes but remain beyond our grasp. This cross-dimensional exchange of knowledge could catapult our civilization forward at a pace that seems almost inconceivable. The implications extend far beyond mere technological gains. Engaging with parallel universes would confront us with fundamental questions about identity, free will, and the nature of choice. Observing the countless ways our lives could unfold under different circumstances might force us to reconsider the very notion of destiny, revealing that the path we tread is just one thread within a vast tapestry of possibilities. Reality itself would transform in our perception, expanding from a single linear timeline into a sprawling web of interconnected alternatives, each as tangible and consequential as the next. Exploring parallel universes demands a monumental leap in our technological capabilities. Advanced particle accelerators, surpassing even the Large Hadron Collider, could detect hidden dimensions or provide the first direct evidence of other universes. Such machines might uncover exotic particles that serve as markers of realities beyond our own. Quantum computing represents another critical frontier. These machines, using quantum bits or qubits capable of existing in multiple states simultaneously, allow us to simulate incredibly complex quantum systems. They could model entire universes, exploring how variations in fundamental constants and physical laws might generate worlds vastly different from our own. Classical computers are incapable of such feats, but quantum computers could run millions of concurrent simulations, offering unprecedented insight into the multiverse. Gravitational wave detectors, refined to extraordinary sensitivity, could capture signals emanating from beyond our universe. Enhancing instruments like the Laser Interferometer Gravitational Wave Observatory might allow us to perceive ripples in spacetime originating from other universes. Space-based telescopes with unmatched resolution could scrutinize the cosmic microwave background radiation, the faint afterglow of the Big Bang, for subtle distortions or anomalies suggesting the influence of neighboring universes. Each of these technological advances brings us a step closer to deciphering the complex structure of the multiverse. Artificial intelligence further amplifies our capacity to probe parallel realities. Machine learning algorithms can process vast amounts of data at speeds far beyond human ability, identifying patterns and correlations that might otherwise remain hidden. AI can simulate countless variations of universal constants, physical laws, and cosmic conditions, helping scientists visualize alternative universe scenarios. It can suggest novel mathematical frameworks for describing the relationships between these universes, and even propose experiments designed to detect their existence. By complementing human intuition with unparalleled computational power, AI could become the most potent tool in unraveling the mysteries of the multiverse, revealing hidden structures and probabilities that would remain invisible to human researchers alone. Quantum computing, in particular, offers revolutionary potential. Unlike classical computers, which operate using bits restricted to 0 or 1, quantum computers use qubits capable of superposition, existing in multiple states simultaneously. This property aligns perfectly with multiverse theory, allowing researchers to simulate multiple universes at once, exploring divergent outcomes in a single computational sweep. As the number of qubits increases, the computational power grows exponentially, enabling the modeling of intricate quantum systems and alternative universe scenarios where slight variations in physical laws produce dramatically different realities. While current quantum technology remains in its infancy, future advancements could transform our understanding of existence itself, offering unparalleled insight into the nature of reality and parallel worlds. Cosmology is also evolving to meet the challenge of detecting parallel universes. By refining measurements of cosmic microwave background radiation, scientists can search for faint patterns or anomalies that hint at the presence of other universes. Enhanced satellite technology and advanced data analysis now allow cosmologists to map this ancient radiation with extraordinary precision, revealing potential signatures of cosmic neighbors. Theoretical frameworks in string theory and quantum mechanics propose that our universe might be just one among countless others coexisting within a vast multiverse. These models provide testable predictions and guide observational strategies, allowing researchers to hunt for indirect evidence of alternate realities. Together, the convergence of advanced particle physics, quantum computing, artificial intelligence, and cosmological observation forms a multidimensional approach to exploring parallel universes. Each discipline offers unique tools, perspectives, and insights, creating a synergistic framework for uncovering the hidden dimensions of reality. The journey toward understanding parallel universes is not merely a scientific quest. It is an exploration of the very essence of existence, challenging our most fundamental assumptions about identity, choice, and the nature of reality itself. By pushing the boundaries of technology, theory, and imagination, humanity inches closer to revealing the intricate, infinite web of possibilities that lie just beyond the veil of our known universe. Furthermore, breakthroughs in detecting gravitational waves are opening entirely new windows into the cosmos, offering tantalizing possibilities for uncovering evidence of parallel universes. As our instruments grow ever more sensitive, capable of picking up the faintest ripples in the fabric of spacetime, we may begin to intercept signals originating from beyond the limits of our observable universe. These faint cosmic murmurs could provide the first glimpses into realms of existence that until now have been purely speculative, hinting at the presence of alternate realities existing alongside our own. The forefront of cosmology is now defined by these daring, cutting-edge techniques, each step expanding the boundaries of what we know about the universe and what might lie beyond it. Recent advances in theoretical physics have also introduced a host of sophisticated mathematical models that offer new perspectives on the concept of parallel universes. String theory, one of the most influential frameworks in modern physics, posits that the universe contains more dimensions than the four we experience: length, width, height, and time. Within this framework, the notion of a multiverse emerges. Our universe may be only one of countless others, each governed by its own unique set of physical laws and constants. Meanwhile, the many worlds interpretation of quantum mechanics presents a vision of reality in which every quantum event generates a branching of timelines, creating innumerable parallel universes. Mathematically, these scenarios are described using complex Hilbert spaces, which allow for the representation of quantum states across multiple dimensions simultaneously. Topology, the study of geometric properties that remain invariant under continuous transformations, has further expanded our understanding of potential parallel universes. The emerging field of cosmic topology investigates whether the universe might possess a complex folded shape, potentially linking distant regions of space in unexpected ways. This could imply that multiple copies of our observable universe exist, each subtly different from the others, like reflections in an infinite cosmic hall of mirrors. The holographic principle, inspired by studies of black holes, pushes the imagination even further, suggesting that our three-dimensional reality may itself be a projection of information encoded on a two-dimensional surface. Under this model, different projections from the same fundamental informational substrate could give rise to parallel universes, offering a radically new way to conceive of existence beyond our own spacetime. Particle physics experiments provide another powerful avenue for exploring the possibility of parallel universes. By probing the smallest scales of matter, scientists are uncovering the fundamental behaviors of subatomic particles and the forces governing them, potentially revealing phenomena that hint at realities beyond our own. Quantum mechanics shows that particles can exist in multiple states simultaneously, a phenomenon known as superposition, which aligns closely with certain interpretations of parallel universes where every possible outcome manifests in its own distinct reality. High-energy particle colliders such as the Large Hadron Collider may even detect subtle signs of extra dimensions or hidden universes. Some theories propose that gravity, unusually weak compared to other fundamental forces, could be leaking into these dimensions, and anomalous energy losses or unexpected particle behaviors during collisions might reveal their presence. Detecting exotic particles predicted by frameworks like string theory would provide indirect evidence supporting the existence of parallel universes. Each advancement in particle detection brings us incrementally closer to unveiling the hidden structure of reality. Observational cosmology offers additional, though highly challenging, methods to seek evidence for parallel universes. Minute cold spots in the cosmic microwave background radiation could be traces of quantum entanglement between our universe and a neighboring one. Gravitational waves with anomalous signatures might result from occasional collisions between universes, producing patterns detectable with current or future instruments. Dark matter, a mysterious component of the cosmos, might even be interpreted as gravity originating from other universes, and careful measurements of gravitational interactions could reveal subtle inconsistencies hinting at these hidden realms. Observing particles that disappear or reappear unexpectedly, or detecting energy losses in high-energy physics experiments could provide further clues pointing toward extra dimensions and alternate realities. Though speculative, these avenues of investigation offer compelling possibilities for the future of multiverse research. The implications of parallel universe theories extend far beyond cosmology, challenging the foundations of knowledge across numerous scientific and philosophical disciplines. In quantum physics, the many worlds interpretation offers alternative explanations for the probabilistic nature of quantum mechanics, potentially revolutionizing areas such as quantum computing, cryptography, and information processing. Biology and evolutionary science might benefit as well. Different universes with varying physical constants suggest new approaches to understanding the conditions necessary for life, inspiring innovative research into the origins of life on Earth and the search for extraterrestrial life. Philosophical and cognitive inquiries are also reshaped by these concepts, prompting deep questions about consciousness, free will, and the nature of reality. Could our decisions be influenced by versions of ourselves inhabiting parallel worlds? How might our understanding of human behavior evolve if multiple iterations of each individual exist across different realities? Ethical considerations in parallel universe research are paramount. Scientists must develop rigorous protocols to prevent interference with alternate realities, ensuring that exploration does not inadvertently harm sentient beings or destabilize other universes. Questions of consent, privacy, and resource management require careful consideration, from safeguarding the inhabitants of other universes to prohibiting the exploitation of their materials or knowledge. Measures must also address the potential consequences of interdimensional contact, including quarantine procedures to prevent cross-universe contamination and psychological safeguards for individuals encountering alternate versions of themselves. Establishing these ethical frameworks is essential to conducting responsible research in this extraordinary frontier. The confirmation of parallel universes would redefine our conception of existence. It would extend beyond theoretical physics to influence philosophy, technology, ethics, and human self-perception. The realization that alternate versions of ourselves may exist, living out divergent choices and realities, would transform notions of uniqueness, fate, and free will. From a scientific perspective, confirming the multiverse would validate certain interpretations of quantum mechanics, illuminate the fundamental forces of nature, and potentially explain the mysteries of dark matter and dark energy. Technologically, the discovery could inspire innovations unimaginable by current standards, possibly opening pathways for communication or even travel between universes. The revelation of parallel realities promises to reshape humanity's understanding of everything, from the nature of consciousness to the ultimate structure of the cosmos, forever altering our place in the universe.